Perfect. See if we have any participants. We have 6 people. Morning, everyone. I hope you had some success last night downloading data or getting things installed. If you haven't, send us an email or a chat, and maybe we can keep helping you out remotely. Yeah. Oh, I see. If you Google small one or they're real small files.
Is that done by year?
Well, you know, year, month, day. Oh yeah. And there's 3 numbers. There's 3 days.
Yeah, I'm always like
the first day is irrelevant.
I'm trying to crazy. I'll download the one that's span.
Yeah. Why did you put that? That's not Scripps. Yeah, it's another.
I'll do the same way.
Yeah, well, I'm not sure where it is, but I think they have it actually broken up by year. The last one is just
Oh.
I don't get that. Go back here.
Right, so I'm Rob Mellers. I'm currently at Lawrence Livermore Lab, which is up in the Bay Area. I used to be down here at San Diego. I actually used to be here at Scripps, where I worked with Dave. Then I went across town at San Diego State for about 10 years and kind of poked along with InSAR. And I still do a little bit of InSAR, but not as much as I'd like. And so this talk is really based on the notes. There was a document yesterday that Dave linked. This is really, I forget which appendix B maybe, Dave?
Yeah.
So all the good stuff's from there. All the mistakes and everything are the stuff I added last night. So are you everybody awake? We're gonna have a pop quiz. Is that okay?
Oh.
Doesn't matter if it's okay or not, we're gonna have it. Then we're gonna have a little bit talk about SAR image formation, what it is, how it works, why. I guess we're not gonna talk a whole lot about lens of synthetic aperture, but some other stuff, and then where the orbits come in, and then some other stuff. So yesterday, Dave talked about what synthetic aperture is, difference between that and real aperture. But I'm sure everybody was sitting here wrestling with shell scripts and trying to download data and all that. So what is synthetic aperture? And Eric, you can't answer. Matt, you can't answer. Anybody who knows the answer can't answer it. So what is it? What's the difference between real aperture and the synthetic aperture, and why do you do synthetic aperture? We have and there's going to be a prize.
Prize?
Yeah, there's going to be a prize. Wow. So the prize will be not one, but two GMT coasters. Okay.
So the real aperture is like you need to build probably very long aperture to make the resolution good. For synthetic, it's like it's a kind of vertical. So as the sunlight pass by, and it's a synthetic all the acquisitions which direct to the same targets, and you make it a synthetic aperture which can be much longer than the real aperture, so you can make a higher resolution image.
Right. So how long is the radar wavelength? Say Sentinel. How long is it? Hold up your hands. So the wavelength.
Like 5.6.
Hold, everybody hold up your hands. How long is the wavelength for a Sentinel? Is it like this? Like this? Well, it's yeah, 5 centimeters. I'm not used to centimeters, but yeah. So it's 5 centimeters. So it's about that big. And you can think a big Hubble Space Telescope that's scaled to wavelength. So for a really high resolution, suppose you just had a 10-meter antenna using what we call real aperture. We're just going to use a straight antenna like a telescope up in space. What do you think the spatial resolution would be? I think it would be, take a guess. Anybody? I think it's on the order, what was it? We've done that calculation. It's like
For
20
the radar or the
for a real aperture, 10 meter for a radar wavelength, something like 20 kilometers or
20
something.
or 40 kilometers?
20, 40 kilometers. So if you just had a real aperture, 10-meter antenna, you could see San Diego, and that's about it. So as, sorry, what was your name? Okay, was saying, the idea is you make a synthetic aperture, so instead of one tiny thing like this, you take this thing and then you move it, and you just add all of those together. So you're gonna make this synthetic aperture, and now you can make it, get the resolution that you want. And so what's the limits on it? Why not just make it 1,000,000 miles? And then you could see everything. You could like track ants or stuff.
The footprint has to overlap
What's the footprint?
the area of illumination.
Right, exactly. So satellites up there, it's beaming stuff down. It's like a searchlight coming down, and that's the footprint. So how long is the footprint for radar satellite? Any guesses? Or how long is this illuminating?
Is that the rectangles we see when we download Sentinel data?
It's related to that. It's actually probably, the footprint's actually less. That's probably, and that's what we're kind of getting into. So the other part is, why is the data complex? And by complex, I mean, why is it real and imaginary? So the data we're getting from the satellite, so, you know, they're sending out a radar beam, that's a real thing. It comes back, and yet you get this data from Alaska or whatever, and it's real and imaginary. Why?
You have amplitude and phase.
Okay, why?
Phase and amplitude.
Okay, phase and amplitude. That's so, and part of it is electrical engineers always do this.
INQ demodulation.
Yeah, and so that's part of it. And so the data radar signal is coming into the satellite, and that's a real signal. And what they actually do is they split it into two. They do a Hilbert transform on it, and they record it as INQ, as radar engineers always do. Now, I'm a seismologist. I'm used to kind of waves coming into a seismometer. We never mess around with imaginary data. So, but then you lose the whole power of the imaginary thing. So, so anyway, the data is complex. As we're saying, it's the phase and amplitude components. What do we care about more? Do we care about the amplitude or phase for interferometry? Mostly phase. We amplitude a little bit maybe for cross correlation, but that. So that's those data that. So the data that you download from ESA or Alaska or wherever, that's real and imaginary. And in fact, we call it SLC, which stands for single look complex. So the complex is, in fact, is real and imaginary. The single look is just, that's kind of fundamental resolution of it, and you can actually zoom that over. So the other thing we talked about yesterday a little bit were modes, and I thought I'd try to Google some better pictures of the modes on there. So mostly when I'm talking about focusing, I'm talking about what we're calling strip map mode, the simplest possible one for satellites are like that. So you've got the satellite flying along, and it's just imaging this strip, a single strip down there. It's just the radar is going and sending out pulses, and you're again. So remember, this is different. This is synthetic aperture. So if you're thinking of an optical satellite is more like click, you just take a picture or something like that. But now you have to collect all this data, and then you have to process it to make an image. So this is what we're calling strip map mode. Basically, it's got pretty good medium resolution. There's also something called ScanSAR mode, which we went into, and that's when it's collecting in strips. And so the Sentinel interferometric wideband, it's that kind of thing where it's actually, this is showing 4, Sentinel has 3, and the radar is actually kind of jumping around. Sends out a message there and then kind of jumps between that. And that way it covers a bigger area. It's lower resolution. And one key thing for interferometry, because it's sending out separate little chirps, they actually have to overlap. Now I think for Sentinel, they're overlapping. Now the older satellite, ALOS, for example, at ScanSAR, they didn't always overlap these, and the downside was it meant you couldn't do ScanSAR. You could only do ScanSAR to ScanSAR interferometry part of the time. And you can actually sometimes combine these. You can, for example, do a strip mode and this interferometry. So you can do interferometry between 2 strip maps, usually between 2 swaths, and sometimes between 2 of these. So you can mix the strip map and ScanSAR. And the last one is Spotlight, where they're actually trying to aim, and they use as kind of an array to image one thing on the ground, and they kind of do that. I don't know much about Spotlight. I do know there are people do interferometry. I know TerraSAR-X, for example. And I don't, have you ever tried it? Maybe I don't see any reason why it won't. Yeah. I don't know any reason it wouldn't work, but I've never tried it. But this is typically the highest resolution you can get. So that's kind of a summary of the various modes. Yeah. Okay. For ScanSAR. Yeah, that's a good point. We haven't really scaled that, as Matt points out. This is actually much bigger than this, typically than the strip map. And yeah, but it's kind of the geometry of it. So, do we focus images for GMTSAR? How many people think we focus images in GMTSAR? Put your hands up. How many think we don't focus images? How many people think sometimes we do and sometimes we don't? How many people are tired of questions and just want to download data? Yeah, so as the slide says, the older satellites, ERS-1, 2, JRS, RadarSat, I guess InSAR sometimes we do, sometimes we don't, right?
Yeah.
We have to run the SAR processor. So what we get is we get what's called level 0 data. You run it through the SAR processor, which is called ESAR for Evelyn's SAR processor. Yeah, so Evelyn was the person who took the JPL code and completely rewrote it in a real language. And then the newer ones, the Sentinel, they come as single look complex and referred to as level 1. And so when you go to the website to download, often they'll ask you what kind of data, and you get this whole long list of data. And it's going to have all sorts of wacky stuff on there, and polarization. Typically what we want, level 1. If you're doing AirSAR, like NASA has UAVSAR, they'll provide it. GMTSAR will not focus aerial data. So this is an example of downloading from Alaska. Alaska, you get this usual map, you draw circles on it or whatever. And in this case, when I'm filtering the data, I always put single look complex on there, which that's what we want to download for Sentinel data. Now, sometimes at the Alaska site, they'll have the raw data, but they won't have the SLC. Usually it'll appear. In that case, you have to go to the European. But that's we don't want any of these other ones, and we don't want anything that's higher than 1. Sometimes they'll have 1.1, for example. And if you forget, you can usually Google the satellite and the data products. And for example, this is Sentinel, where they go through strip map mode, the raw data, single look complex, and what And note here it says level 1 right there. So if you're getting confused about what level and what the data is, usually you can Google around and find it. And so we care about the strip map and the interferometric wide swath mode. I don't think this will probably work, the extra wide swath mode. Yeah. So how exactly does it focus? So as we were saying, satellite is flying along the orbit, it's sending out pulses, and you're trying to make an image like that. And so it's not looking straight down, it's kind of looking to the side. It might be looking to the right or to the left. And then there's various angles and geometry that you have to worry about. So the footprint at any given moment is what's illuminated, and this is the swath of that. So how is it focused? Well, this is kind of a, let me see if I can, yeah. So there's basically 3 major steps, and this is for strip map. Well, it kind of applies for the others as well. This is really designed for strip map. The first thing is the radar, when it sends out a pulse, it doesn't send out a single, this is kind of time series. You might think it sends out a single thing like that. It doesn't. What it sends is more of a chirp. And by a chirp, I mean something that I draw very well. It starts out low frequency and goes high, or maybe it starts out high frequency and goes low. So it sends out this kind of, say, anyone done a better imitation of a chirp? A bird chirping. Imagine a bird chirping. And the same trick is used in seismic as well, a viper-sized truck. Anyone ever seen a viper-sized truck? Thing that vibrates. Nodes start out low frequency and then they go higher because it's hard to start something vibrating really high. With radar, it's not quite so tricky. So it sends out a chirp pulse. And when you get the data, the first step is to get rid of that chirp. And so you do that, you know what the chirp is because someone programmed it in. You take those parameters and you deconvolve it. And by that, you just take the FFT of both and apply them together and then do the inverse. Now, the problem is, if you look at an image like this, it looks pretty simple. Everything's nice. The radar, the range is exactly perpendicular to that. This is all straight lines. Is the Earth a flat? Hopefully no one's going to say yes. The Earth is curved, and so all these things that appear as straight lines on here are actually kind of curved because you're looking down at a globe and the satellite's going there. So you've got all this curvature in there, and that makes life difficult. And so you want to take care of that curve and make things straight, so there's a kind of interpolation in there. And then the next step is you want to take all this image information there and compress it together. And that's called azimuth. I'm going to skip this. Well, that's the azimuth. So first, so is everybody clear on range and azimuth or SAR? What direction is which? If I'm saying satellite's going this direction, which is azimuth, where's range? So azimuth is in that direction. Range is perpendicular, close to perpendicular there. And so we go through, we do that, and then because it's curved, we do this range migration to try to compensate for the curve, and then we take it along the azimuth. And that's what the SAR processor does. And this is just a description of what the actual chirp looks like. So rather than what I drew on the board, this one, the radar chirp, starts out high frequency, then it goes low, and then it goes high again. And the middle of this thing, for the older ones, there was something we worried about called Doppler centroid. So if you're using ERS and ERS1 data, you have to worry about that. I don't think anyone here is doing that, so let's not worry about that. I think all the SLCs are done to a 0 Doppler. Is that right? I think, yeah. So this is what we know the chirp is. So you take that, and that gets rid of the distance and range. And now this is the part of how you get rid of the kind of the curvature. You've got the curvature of the Earth. It's basically an interpolation. There's some math involved, and this is in part, in here is a V and location. And so during all of this, you have to know how fast the satellite is traveling and where it is. And that's where your orbit information comes in part. And you also get it later in the phase. And then finally in azimuth, you're going along the direction the satellite is traveling, you're collecting everything. So this is probably kind of, and somewhat surprisingly, in azimuth, you get the same kind of chirp. So it's a lot like the range compression, slightly different though. So if you're writing code to do this, basically it's actually pretty simple. You take an FFT of the information in range, you have the known chirp, FFT of that, you convolve the two together, you do inverse FFT, now you break it up into patches, and you do kind of the same process in the other direction. There's some interpolation in there. And so the program in GMTSAR is TSAR, and the parameters for all this are in the PRM file. So if you look when you're doing the processing, or there'll be something called a PRM file, that's just ASCII, and that has a lot of the information, the length of the chirp, the slope, and some of the other information, if you're doing that.
So one question, what part of the processing is done in the radar and what part of the processing is done?
The radar really doesn't do any I mean, what it does is it takes the real radar signal in there, it shifts it 90 degrees and takes the IQ components,
That's what it brings down?
and that's what comes down. I mean, the newer ones probably might do some compression. I don't know. For example, the original ERS, I think they sent it down as 8-bit data. So it was.
So the raw file that can be downloaded, that's below the SOC.
Yes, exactly. The raw, yeah. It hasn't been focused at all. It's the raw data. This is kind of let's see. So this is an example. Actually, it turns out when you go in this mode, that doesn't really, there's a whole animation there, doesn't work. So this is an example. So here's what the unfocused raw data would look like. This is kind of an amplitude image of the raw data. This is over Pinion Flat, which is, I don't know, 50 kilometers north of here. Range is in this direction, azimuth is in this direction, and you really don't see anything at all. And then what you do is in the range compression, you then convolve it with a chirp in this direction. And now, because you convolve it with a chirp, these vertical line, I'm not sure what that word is. What is that vertical line?
It's missing data.
Yeah, I think it's missing data, so I can ignore that. Because we've convolved it with chirp, all this, and what this had, there's a corner reflector opinion, that's this thing right there. And the property of this is that no matter what direction the radar is coming in, it gets reflected back. So it shows up as a very bright point target. And so the information in the raw data, the data representing this is spread out across this whole scene. You do a range compression, and now all that has been isolated to this. And it says, okay, the data from this thing is located at a distance, whatever it is, from the satellite. It shows up at one particular range. We now know that it is located at one different range, but we don't know the kind of the azimuth of it. Yeah. No, what we've done, all we've done there is we've convolved it with the chirp. Yeah, so there was a chirp in there, and you can't really, because there's a bunch overlapping it. So all we did was we took a chirp, we convolved this data with a chirp, and this popped out.
And that line is really curved.
Yeah, this is actually curved. You can't really see it. Well, actually, it's, yeah. And then we took that range compressed image, and now the idea is you want to go with the azimuth, so there's a little bit of interpolation to make it less curved that you can't really see, and you get these points, and that's the focused image. So that's really what focusing does. This is just an example. I don't remember exactly what the, yeah, so this is an image of that. And just a few notes about radar images, you're always looking at one point. Areas that are perfectly flat like water, the rays hit it, bounce off, they appear dark. If you have mountain faces facing you, they appear bright. Away from you is dark, and there will be places where there's actually shadow. You're not looking straight down, you're looking at an angle, there'll be a shadow zone in there. And so all of this focusing requires an exact knowledge of the orbit, which is why we have the orbit files, and that's why we worry about the orbit a lot. And if you have a very good orbit, which we do now, you can now, just from this data, estimate exactly what these points are without reference to a DEM. And that's what we do in GMTSAR. You take the orbit and you calculate exactly where that point is from the orbit, and that's how you correct things. And I think, okay, so just one little last note. You can do interferometry from an airplane. And so NASA, for example, has something called UNAVCO. It flies around. You can write proposals and get it to fly over an area that has a high resolution. But you can imagine for a satellite, it's moving pretty steadily. Airplanes, you get a shift of wind. It's moving back and forth. It's much more complicated. You can see they want to try to keep it in its tube, but you know, there's all sorts of, the pilot sneezes or something, or the wind blows, and it varies. And so that makes it much more complicated. So they have their own special processors for that. And I think if the weather is bad enough, you can't even do that. So it's possible to do, but it's much more complicated, and we don't deal with it in GMTSAR. And I think typically for NASA, you'll actually get the interferograms from them. And this is setting up for where you're going to interferogram formation next, I think. So this is just, remember, this is our raw data that we focused, or this is the phase image. The two scenes, you can't see anything, but when you difference them, you get that, and that's what Dave will talk about. Homework problem. So complex, we talked about that. Why is it done in patches? Just because you want to, there's approximations in there. And then we went over the chirp. And if you want to do 4, 5, and 6, please go forward. So that's it. And there's a typo here on this slide, which I'm not going to go into. So thank you. Questions, comments?
Could you comment on the along the azimuth compression again? Is the antenna sweeping on azimuth? Is it like a phase array, or?
For the, let's see. So what happened when we went in this mode? It kind of emitted some of the. Actually, didn't. Okay, we lost. Yes, there was the. He had this nice animation of how the focusing was working, and it doesn't really work on this mode. So for the spotlight, it's more of a phased array. So
so the example that you presented for the corner reflector, was that the
so this actually, the spotlight mode, where you're actually, they don't actually move the antenna, they're summoning electronically on that. That's where it's acting more like a phased array on there, or what I think of as a phased array.
What was the corner reflector example? Was it the middle, more like the middle?
Let's see, where are we? That one, or?
Yes. So when you're doing the focusing, is it like the middle example on the cartoon of the 3?
No, this would be the one to the far left. I mean, it's sort of similar. The ScanSAR is basically the same. It's just a little bit more complicated. You do the same thing. The ScanSAR is a little bit, because you get bursts of that. It's not kind of a continuous.
So does the footprint from the InSAR, do they aim to be as circular as possible, or not really?
It's kind of what you get, I think. I don't think it's really circular at all, really.
So it's not necessarily a dish. It could be like something else. If it's a dish, I guess it will be somewhat.
It's, I mean, it looks like one of these tables, kind of.
Oh,
through
okay.
these tables, it's what it looks like. So it's just, yeah, it's not a dish. It's really a flat antenna. Other questions, comments? Did I run over? I don't know. All right.
Maybe we should take a short break. Does anybody need help with downloading data or getting things to run? Or, okay. Oh, you don't need it. Okay. It's downloading now.
So when you're downloading something, if you want to get started on creating your Interferogram, regardless of waiting for that, what steps can you take for making it the most efficient? So once it's downloaded,
you can make your DEM, so make that topo directory, find the area that you want, and make a DEM, put that in there. That'll take a few minutes to do. And then the other thing you can do is, if it's a new example, copy the config file from another example. I guess you don't have to do that anymore. Yeah, the config file just create. Yeah. You can, but you can do it.
Well, I guess I think that, well, you can solve it with the church. I mean, to me, what you can do is you have the data, like Microsoft, you can evolve it with the representation. And that gives you the cloud. No, you should have ideally you have the perfect oh no, it's not here. Well, actually, the LCD. Yeah, it's not yeah. You're replacing the.
Uh-oh.
It's not, well, it turns out the answer because you're really looking at what effect you're going out and getting sure. You can think of it, you've got a point, you're approaching the point, so the aperture increases the frequency or decreases down. Yeah, you can actually go from high to low. You're right above is zero, and it goes high. So imagine if it turns out it's a sure but yeah. No, each satellite. As far, yeah, as far as I know. I mean, the estimate curve is going to depend on like where you are. That's why you can download well, I mean, all the orbit codes and so you have, if you look at you have things calculate the actual azimuth. So you've got the satellite here, you've got to calculate the direction and the relative yeah, so the orbit is get to, yeah, four numbers same. Yeah. Again, it's calculated, yes. And so it's more important for the upper phase. If you just process you get away with another overstop. Do they use water along the arm? I don't think so. There might be zero alpha. I don't think there's SLC. So for ERS, I always process. I always use the look up and then satellite.
Oh, this is pretty sweet.
Oh, now I've really messed this up. Wow. Okay. Uh-oh. Does anybody know how this PowerPoint thing works? I'm completely baffled here. Like,
Years ago, my office PowerPoint was not working, and I did a presentation in
GMT, okay, yeah.
Scripts for each slide.
Maybe I should make it into a PDF.
PS to PDF.
Yeah, I could make it into a PDF. I'll try that. Save as. Save as PDF on the desktop.
Oh. I thought you were like typing in GMT while you were giving the presentation.
I made the slides in PDF.
Did that work? What's that? Oh, I did? So, oh, shoot. File. Save as. Oh, yeah. PDF. There we go. Export.
Things are slowing down. They're hitting the network.
Everybody's downloading data, huh? Wish I could get to the desktop. Oh, here it is. Oh. Now what do I do? That's PDF. View. Slideshow. Oh. Can the remote people see this, do you think? Is it okay? Okay, I just made a PDF and it's better. That's the solution. Okay, so, oh, what happened? Okay. So why don't I get started here? I want to talk a little bit about the theory of interferometry and what are the signals that you see in an interferogram. It's not all surface deformation. There's other things that you see. So this is an appendix in that document, Appendix C, and we talked about this yesterday. Here's a little homework thing. What is the algorithm that's used to transform a point on the surface of the Earth, latitude, longitude, and elevation into radar coordinates? Does anybody remember how to do that? It's really brute force. Brute force algorithm. So you have some point on the surface of the Earth. Here's the point. Yeah. That's the name of the program, yeah. And all it does, it's really brute force. It just takes that point, lat, long, height, and it flies the satellite using its orbit. And it finds the closest point. It just keeps computing the range over and over again, homes in on it with a least squares thing, finds the closest point. That's the range, and the time or the azimuth of that closest point is the azimuth. Really brute force. Very simple. Okay, here's sort of a trick question. The SAR images today are all focused at something called zero Doppler. So imagine a satellite's flying overhead and you can hear it, you know, and it has a certain frequency, whatever, 60 hertz. And as it's approaching you, you're going to hear a higher than 60 hertz, and as it goes away, it's going to be lower than 60 hertz. What is the range when it's exactly 60 hertz? Is that, why is it minimum range? Does that make sense? I mean, it's sort of obvious that. So it's coming along like this. It doesn't matter if it's diving towards you, whatever. When the minimum range hits, that's where it's zero Doppler. So by definition, those two things are the same. Rob just talked about this, frequency modulated chirp, basically because the engineers can't send out a pulse. They just can't send all that power at once. So they distribute the power over some time and make a chirp. And then this one here, you'd have to do a MATLAB script to do that. Okay, so today we're going to talk about something called the critical baseline. And to do interferometry really well, you want to have the reference and repeat tracks be exactly along the same orbital position. What does it mean to be exactly the same? Is it 1 meter? Is it 10 meters? Is it 100 meters? There's a thing called a critical baseline, and when that baseline gets to be beyond the critical baseline, you don't get any phase coherence anymore. And there's a simple formula for that you can derive. Here's another thing that is sort of important. If you're in a really mountainous area and you're doing interferometry and you're measuring, here's the satellite here, and here's the mountains like this. And the range to the top of the mountain, if the range to the top of the mountain is shorter than the range to the bottom of the mountain, the phase is going to get all screwed up. It's called layover. And so when you make an interferogram, sometimes if the mountains are too steep, you won't be able to connect the phase between this point. The pure geometrical. And when you look at a radar image, you see the mountains leaning towards the satellite, and that's part of this. It's called foreshortening. So it all depends on the slope of that mountain slope and the look angle of the radar. I talked about this yesterday, master and slaves. When you're doing batch processing, you have one master, many slaves. You geometrically align all the slaves to that one master. We'll talk about batch processing later. I don't see Katya. Katya hasn't come yet. Okay. She's up at JPL. She's driving down today, I guess, and she's probably in traffic. I think she's going to talk about batch processing, or is that you? You could do both. You could do it. Okay. So batch processing is really what you want to do when you want to make time series and look at time evolution of a volcano or something like that. So then you have one master, many slaves. But then when you make interferograms, it's a reference and repeat. So you could take two of those slaves and make an interferogram. So there's many more interferograms than you have solar images usually. Maybe 5 times more. Okay, so here's back to interferometry. Maybe I'll go to the next one first, and then I'll go back to the math. So as Rob said, when you focus this raw data, you get a single look complex image. And if you looked at the phase of that single look complex image, if you just, how would you get the phase? Let's say you had real and imaginary numbers. How would you get the phase of that? Yeah. Exactly. Arctangent imaginary over the real. So you would just take these numbers in your single look complex image, take the arctangent. You can do that in GMT, GRD math, real simple. And you'd make this image and you'd look at it and say, oh my God, that looks horrible. It looks like random noise, just completely random noise. And it is. The phase between one pixel and the next pixel, there's no correlation. And then if you do that in your repeat image, it looks exactly the same. And when you difference those two phases, you get this kind of a interferometric signal. So these two have exactly the same phase if all the conditions are right. If everything's right. So let's go back. So a single look complex image has an amplitude as a function of range and azimuth. X here is range and azimuth, a vector coordinate, and it has a phase, e to the I phase. And there's the X there, the range and azimuth. And so when you make an interferogram, you take the repeat image, the complex numbers of the repeat image, and you multiply by the complex numbers of the reference image. And it's like it's just like multiplying these two things together, and you see that you get a phase difference here. This is a complex conjugate. So we took the negative of the imaginary part. So it's a phase difference, and you get a real plus I imaginary. If you look inside of GMTSAR, there's a thing called phase diff, and it outputs a real array and it outputs an imaginary array. Really that simple. And then what it does is it, at one point, I think this is in GRD math. Is this in GRD math, Eric, the phase extraction? I think it is. We just put in the imaginary part, and you put in the real part, and you say atan, out pops the phase. So it's all being done basically in GMT at this point. Phase diff outputs the real and imaginary. And what happens also is that this can be pretty noisy. A single look complex, really high resolution. You have to do everything first at full resolution. It can be pretty noisy. So then we'll come back and filter these real and imaginary numbers before extracting the phase. And this is where sort of the art comes in. You want to do the right amount of filtering for each image so you get the most information out. And it's a matter of taste. And we can tune those parameters in the config file. Okay, so we do make an interferogram. But what are we looking at? We're looking at a whole variety of signals. The largest signal is the curvature of the Earth. It's just that when you can go through I call it the triangles. You draw a bunch of triangles, and you'll see a phase ramp in range simply due to the curvature of the Earth. Now, we know the radius of the Earth. We know the curvature of the Earth, so we can remove that part pretty accurately. The next biggest signal is due to the topography of the Earth. And if you have a pretty good DEM, like the SRTM DEM, you can remove that signal. Now, these aren't always perfect, so you might have some residual phase due to an error in this. The third one that you're hoping for, most of us, is the surface deformation. And this could be almost anything. It could be a huge earthquake, but it could be a very small creep on a fault, something like that. Down here is the orbit error. This is getting to be smaller, but if you don't know exactly where those reference and repeat orbits are, you have to know within centimeters, because you're differencing the phase of those two. You can typically get a ramp in your interferogram. This is becoming less of a problem today because we have better orbits. This is a real problem, the ionosphere. And it depends on the frequency. At very high frequency, like C-band, the ionospheric problem isn't so bad. But when you go to L-band, it's like 16 times worse. So when you make an ALOS interferogram at L-band, you're mostly looking at the ionosphere, mostly. It's really hard to get rid of that ionosphere. And NISAR, the satellite that's going to go up, the NASA one, will have a way to get rid of that ionosphere. It'll have two frequency bands, and it will use the physics of the dispersion through the ionosphere to remove the ionospheric signal. And that's exactly what GPS does. GPS has two L1 and L2, and it uses those two to remove the ionospheric signal, which is huge. It's meters of delay. So the ionosphere is really bad. You can see waves, you can see all kinds of weird things. Rowena Loman showed me one in, I don't know if you guys saw this, it was in Saudi Arabia. And there's these ionospheric bubbles, and they bubble up and create these round circle things in your interferogram. You saw those, yeah. Really strange. And first, we didn't understand it, and then she talked to an ionospheric physicist, and they said, oh yeah, those are common things in the ionosphere, these bubbles that come up. If you have a tsunami, you can create ionospheric waves. The ocean waves will get amplified all the way up into the atmosphere, and you see the ionospheric waves. So the ionosphere is a real big problem.
Does it vary by latitude?
It varies, yeah. California is not so bad, but if you're on the equator or near the poles, it's really bad sometimes. It also varies by year. So right now we're coming into a solar minimum, but every 11 years the sun goes through a cycle. And if you're at the maximum of the solar cycle, the ionosphere is more of a problem. So, so the ionosphere is a real problem. Now the big problem, when you make all your interferograms, you're going to see tropospheric delay in every one of them. You'll look at these, you'll see some phase signatures, and you'll say, oh, maybe that's deformation, but it's not. It's going to be the troposphere. And the only way to get rid of that is to average many, many interferograms, stacking, that kind of thing. People try to use weather models to correct for the troposphere, but the weather models don't have enough, usually have enough spatial resolution to do that correction. So there are all these signals, and we're usually trying to get out the surface deformation. I'm not going to go through this, but I'll give you the highlights here. We would like to have the reference and repeat orbits be in exactly the same place, to within centimeters, say. If they were within centimeters, our life would be really easy. But you can't drive the repeat track that accurately. Most, the satellites now, Sentinel, usually are plus or minus 50 meters, which is pretty good. They're getting those repeat orbits within a tube that's about 100 meters in diameter. But in the old days, they couldn't control the satellite orbits that well, and these might drift off to 1,000 meters. And then things start to decorrelate. You get more sensitivity to topography. So what I'm talking about now is maybe the old days. We don't have to worry about it so much anymore. We used to make these plots of baseline versus time, figure out which pairs have short baselines, make interferograms. Now, we just assume that they're all, with Sentinel, we assume they're all good interferometric pairs. So at some point, you could go through this little bit of math, and it's just triangles, and you figure out, given a certain baseline and certain range for your reference orbit, what's the increase in range on that leg of the triangle? Just trigonometry. And what's important is how does that range vary across the image? And so when you take the derivative, you go through this little bit of math, and you'll come up with this thing called the perpendicular baseline. That's this component of the baseline is what scales the topography and the Earth curvature and everything, perpendicular component. And so you always try to minimize that perpendicular component of the baseline. And again, for Sentinel, it doesn't matter. But if you're doing ERS or NVSAT, you'll find that some images won't interfere because the baseline's too long. Okay, so you make your interferogram, you don't do any corrections, and it looks like this. It's just a bunch of these, the white here is plus pi, and the black here is minus pi, and these fringes are going very rapidly in range. Again, that's due to the Earth curvature. And you see some other stuff in here. And so let's remove that Earth curvature part. Oops. We can come up with a formula. Let me go there. So if we remove that Earth curvature part, we get something that looks like this. Here's the Salton Sea. You see there's no phase coherence in the Salton Sea because the water has moved between the reference and repeat images. What we're looking at now is the phase just due to the topography. We removed the curved earth part. And so in fact, you can make a really good topographic map by just simply unwrapping this phase and scaling it and making topography. And that's how the shuttle radar topography data were created. They had a fixed baseline in the space shuttle, and they flew over the Earth and made these kinds of interferograms, unwrapped the phase, made topographic maps. So, but we don't want topography, so we're going to remove that. But if you just remove the curved Earth, you're going to get the topography. And in an ideal world, the phase at the shoreline of the Salton Sea should have been 0 because it's all the same elevation. But it's not 0 because of other errors, atmospheric delay, ionospheric delay, orbit error, whatever. The space shuttle didn't have that problem because they were measuring this phase difference at exactly the same time. So both paths were looking through the same atmosphere. So they didn't have to do an atmospheric or ionospheric correction. They had to correct for the tilt of the antennas. Okay, now I sort of skipped this part, but I'm going to do this sort of intuitively. If you increase the baseline, this fringe rate goes up, the number of cycles per pixels. And right now it's maybe 1 cycle every about 10 pixels. If you zoomed in, you could see there's 1 cycle per 10 pixels. Well, what would happen if it was more than 1 cycle per pixel? What would this look like? But yeah, it would look like noise. It would be a big mess. So if your baseline is too long, you'll get more than 1 cycle per pixel. And if you get more than 1 cycle per pixel, it's going to be completely decorrelated. And that's called the critical baseline. So, and it just depends on, there's a formula here. The critical baseline depends on the wavelength of the radar, the range, the speed of light. This is the chirp, this is the length of the pulse, and this is the incidence angle, the tangent of the incidence angle. So what is this telling us? First of all, we can't really control the range. The range is just the distance from the satellite to the ground, 850 kilometers, something like that. Speed of light, we can't change. The look angle is going to be about, 40, 30 degrees, something like that. The only things you can change in this formula are the wavelength. And what it says is that a longer wavelength is better. Longer wavelength, the critical baseline is longer, you don't have to control the orbit so much. So C-band is shorter than L-band, so L-band is better by a factor of whatever that wavelength difference is, maybe 2 or 3. And it also says that a shorter pulse is better. In other words, if you make your pixels smaller, higher bandwidth, you get a longer critical baseline. So this critical baseline is a function of the radar. And for NVSAT and ERS, with 16 megahertz, that's this pulse length, the critical baseline would be about 1 kilometer. So in the old days, when we make interferograms, we would make a baseline versus time plot. Any interferogram pairs that were had baselines longer than about even 200 meters would be sort of, you throw them away. But with ALOS, what has the L band, you could go to much longer critical baselines and still get good interferometric results. So now with Sentinel, I don't know what the critical baseline with Sentinel is. The range resolution is better by about a factor of 4. I think about 4 times better. So that would make this number 4 times larger. It's probably about 4 kilometers. But you'll see that with Sentinel, they control the baseline within 100 meters, maybe 200 meters on the outside. So we never worry about this anymore. But if you're going to go back for the old data, you have to worry about that. So what you could do is, if you want to recover topography, you might select interferometric pairs that have a moderately long critical baseline, and then stack those and make a nice topography map. But if you want to do deformation, you'd select your pairs with short baselines. So again, this is the old days, but if you're going to go back and look at ERS data, here's that perpendicular baseline as a function of day starting in 1992. So this is about a 10-year-long mission. And you see these baselines are wandering all over the place, up and down, 600 meters. These red lines here are big earthquakes. This is the Landers earthquake and the Hector Mine earthquake. So if you wanted to make a good topographic map, this is before SRTM. The SRTM data became available in 2000, was it? I think it was about 2000. So this is going back 20 years already. Okay, we're getting old. Sorry. There was a time before SRTM, but now we have SRTM. So anyways, we used to make our own topo maps. And you'd make a topography map like this, and then you'd use that to correct the phase of your difference data. And then if you want to change interferograms, you would go and select all the pairs that have short interferometric baselines, but maybe long temporal baselines. Here's one example that spans 2 earthquakes. And in the Mojave Desert, you can do this. It's really dry, so you can make long time span interferograms. And what you see are the fringes due to the Landers earthquake. Remember, there's 28 millimeters per fringe here. So we're sort of out on the perimeter of the earthquake. It's over here somewhere. And then there's the Hector Mine earthquake. And then what happened was during those earthquakes and also between the earthquakes, there was creep on the San Andreas Fault. So you can see a little bit of fault creep going on. Okay, so we need precise orbits. I said that way too many times. We'll talk more about batch processing, but again, for batch processing, you get a whole bunch of single look complex images and you put them in a stack, and they're arranged in range and azimuth and time, and you pick one master. Nowadays, we usually just pick the first one as the master. In the old days, we'd pick one in the middle here. And then we'd align all the slave images to the master, and then you can make interferograms from any pair of slaves. Okay, a little bit about correlation. So basically, there are 3 types of radars in orbit right now. There's the X-band, 2 centimeter wavelength. There's the C-band, which is 5 or 6 centimeter wavelength. And there's the L-band, which is like 24 centimeter wavelength. And each of one has sort of its own purpose. But one thing that happens is that the shorter wavelength radars, like the X-band and the C-band, the radar waves don't penetrate through the trees, the foliage, to hit the ground, to hit stable reflectors. They reflect off the leaves and branches. And what happens is those things move between the reference and the repeat, causing a decorrelation. So here's a real classic experiment done by the JPL folks using the space shuttle, where they had a C-band and an L-band radar running together over Kilauea. And you see what's going on here. First of all, the fringe rate, we're looking mainly at topography. The fringe rate here of the C-band is higher than the fringe rate of the L-band simply because of the wavelength. So that's the first thing. So C-band is more sensitive to topography and deformation. But you see all this area here where there's no phase information. And if you go to Kilauea, you'll see this is all sort of foliage. This is all lava flows, very hard rock, nice reflectors. But you see the L band provides continuous phase over the whole thing. So in this case, L band is better than C band because you're getting some phase recovery. But of course, for the ionosphere, L band's worse than C band. So there are trade-offs between these. Another example is an earthquake here in the L'Aquila earthquake here in Italy. Let me go to the L band one first. Here's the earthquake, magnitude 6.3, really nice coherence with this L band ALOS 1 data, 23 centimeters. But you only get one fringe. So this moved 11 centimeters, sort of. That's sort of half. One fringe is half of the wavelength of the radar. If you go to C band, you get more fringes, but then you lose coherence in all these areas. And so it's going to be hard to unwrap the phase. We'll talk about that later. And then if you go to X band, you get almost nothing. X band is really good if you're in cities and places where there's stable objects, but when you're off in areas with foliage, you don't get much information. Okay, so if there's any questions? Oh, you guys can answer these. Why is the critical baseline for ALOS more than 10 times longer than for ERS? Give 2 reasons why. The wavelength, yeah. And yeah, the time is smaller. The bandwidth is higher, so the pulse is shorter. What happens to the phase of an interferogram when the slope of the topography is facing the radar exceeds the incidence angle of the radar? And I drew that on the board over there, so yeah. Master slave, we went through that. And I don't know what equation C8 is, so. So I don't know if there's any questions. As you start making interferograms, you'll see all of these issues, L band, C band, and decorrelation, and tropospheric delay, and orbit error, and
Are there any platforms that are multi-band?
Yeah, well, NISAR is going to be. NISAR is the NASA one will be L band and S band. S band is halfway between C band and L band. And yeah, it'd be a great thing to do. What's that?
How exactly do you do that? So they can just simultaneously set band and
I think they're just 2 different radars on the same satellite, and they don't interfere because they're different frequencies. But, yeah. Yeah. Yeah, yeah. Yeah, yeah. Okay, what's being made is the Earth curvature, the topography. Those 2. That's in that. So Eric's been working on what's called split spectrum. I don't know if you're going to talk about the split spectrum, but because the speed of the radar pulse through the ionosphere varies as a function of wavelength. If you split your band into a short wavelength and a long wavelength, you get a different delay, and you can make a map of that delay difference and use that to create something called the total electron content. It's the integrated electrons, and then you can correct the interferogram for that. And that's how GPS is done. And that's how NISAR will be done, yeah.
Right now, on the program on the information we are making on the part coverage and does it have any effect on the final results in terms of actual information?
So the question is, we're just making the Earth curvature and the topography correction, and does it have an effect on the results? It can. It depends on the baseline. If the baseline's really short, these corrections are pretty small, and you're pretty much seeing surface deformation. But as the baseline grows, any error in your, we know the shape of the Earth, but we don't know the baseline precisely. So any error in the baseline or in your topographic map will go directly into this deformation point. Yeah. Sometimes with Sentinel, you see interferograms and they look a lot like topography, but it's not topography. And I don't know if I'll talk about this now. We're going to talk about atmospheric stuff, but anyways, when you have here's the reference, and here's the repeat. And let's say you have some topography like that. It's the same topography over here. Sorry, I didn't drop it. And this one has no atmospheric problems. Right? All the way just look out of that. This one has some layered troposphere delays. And so the delay at the top of the mountain is 0, but at the bottom here is 2. And so when you make your interferogram, it will look a lot like topography. So this happens at volcanoes all the time. Yeah. Hard to correct that.
Even with the Sentinel and all those, it will be very yeah.
And we know how they track the orbit. You measure the orbit in some way.
For all these satellites?
For all these satellites.
They use GPS. So every satellite has a GPS, 1 or 2 GPS antennas on it. And so it's,
But they're not tracking from ground radar.
no. Well, here's your that. And here's your satellite. Here's the GPS satellite. You got a bunch of them. They're high. And the SAR satellite is down here. And so you have all these ground stations tracking the GPS satellites. They're all tracking GPS. Like that. And then this SAR satellite is looking at the GPS signals. Getting tracked out. There's no atmosphere in this path. GPS is really good. Okay, so I guess we're going to take a break for an hour, but keep working on your projects. Again, we're going to have presentations starting tomorrow, so we have something to show.
Producing data, but I don't know yet. It's gonna work. Maybe it's background. Now we're running.
When you were off, I don't know whether it's still on your.
Oh, for topography, they're not there. Just download, you make a case here at the focus website. It took a while. took over like maybe 45 minutes.
Oh, and you prompt you, right?
The orbital file for Sentinel, they have different extensions than for the Ridgecrest example. These ones are called OPER, OX, but then there are POERB, and this one says RESORB. Are those okay, or they're different?
I think that's the thing I told you earlier. We have the orbit with predicted orbit, which last after. Then they also have the high resolution. So one of these is the better one. Yeah, I'll Google just Google Sentinel orbit. Okay, so we're here.
So did I download the wrong one? They all say POERB.
Go back to the original.
Oh, these ones are precise. So this one
Yeah.
the good ones.
So, yeah, this is a person. Okay, this is the one.
Oh, for Ridgecrest, you guys did it quick. Like based after the first cover came out. The Ridgecrest one is the one that had the.
I use the
Sorry. Okay, so the Ridgecrest was 2019.
Yeah, you see, it's July. And these, I think these are.
Oh, and the earthquake was in. Oh, the repeat frame is from July.
Yeah, the first one is July 4th. The last one is July 17th, 16th. So,
Those are immediate orbits.
yeah, these are probably the kind of predicted. And these are like, what you can do is,
Where can you find the predicted ones?
so you have to go out. Okay. So just Google, well, just Google again. Sentinel orbit. So this one is the precise. You go to this one.
Oh, this is Sentinel.
You can have it right here.
Oh, this is Sentinel 1. Oh, there we go.
Show this, but predicted. Yeah, so the one you have actually it's called a
Yeah.
well, for the first earthquake, I think you
Sometimes
I'm just looking at so the latest one is July 29th. So this one actually so in the precise one, I can see what there is. Yeah, the July 4th and 26th. So I think
So this is the time that they upload them, the first timestamp. It's where
this
they
is
put
the
them up.
yes, this is the time they upload them. These are the time that covers the upload. So the latency for these precise one you can tell, right? This is July 6th, almost 20 days. This predicted only for the last 7 days. So then there's like 14 days in between. Where the FNU probably use this one. I don't know what. This is probably somewhere, something in the middle. It's better than the predicted one, but it's worse than the precise one. But once you you can tell if
Yeah, we're gonna go and research.
the orbit has a problem.
Well, this one are pretty new.
Yeah, this is new. So this one, that's what you have for the express. Yeah. This is probably the best you can get for now for that pair. But maybe let's say like 2 weeks later, when you come back here, you will look into this predicted orbit. Okay. Then you get the precise. No, sorry. The precise orbit. You will get the best orbit for that pair. Okay.
Yeah, let me book my face.
Yeah, usually you can tell if there's orbit problem, because if the orbit is really a problem, you'll see long wavelengths ranges go across the image. Usually there's a way to render them just by fitting into a plane. Yeah, so basically if there's orbit error, your image is tilted. How you do it is
Do you like deep trend that
it works fine if your image field is small compared to the image.
We were just wondering if you're gonna be here.
Yeah, so what I think for this one, I don't want to mess up, was that I kind of copied the script over from the script, just tweak it so it's a little bit clearer for me because I'm not very familiar with it. But when I look at the express example, the readme, what is this for? This will be done after the fact, the coherence and the high res.
Yeah, we had.
I'm learning like people.
And I learned some jokes.
I should have
Me too.
And then the GMT guys.
They sound like
Oh, you did?
yeah.
It's a ASCII file. You can just read it. You can do it.
Oh, but I don't know why you would put PWD first and then solder the TSA. I don't know if you have the, I don't know if you have the directory.
So now so basically you're going to fix so let's say if you have 100 pictures, this one will average out.
Okay, like a low pass.
It will skip so basically make the image smaller. So the full resolution one, so you don't get all the pictures.
There was talking yesterday about running that before overall.
Yes.
So I thought that this was for that, but it doesn't make sense. Because this will be too late.
So filter that is one of the commands included in that. So basically you're doing this part again. So you do If you look at the interferogram script, this filter does it. This is one of the steps. One of the steps that controls. So basically, you are doing this step.
What's the name of the script again? Depends on your for Sentinel. This doesn't call filters already. This might call a script that runs. So might be
Oh, I see. So filter maybe is one of the it's not counting that.
It's magic.
It's a serial step. So SRTM1 is and SRTM3 is available. Aster is 30 meters long. So you're asking how you can find that? Yeah, so yeah, it has to be here. Otherwise, you'll have places where make it bigger. And this can be twice or three times bigger. It doesn't really the code will, the holding process. Yeah. The holding takes the data. So if your file is bigger, you're going to slow down this process. How do you link the location? So on the map, it will show that. Yeah, well, you have to find that one is turning the word. Well, these are all the same dates. I have to find another date. Usually 12 days before that. November is the yeah, you can change this to like October 20th. Also, it helps. Are you looking for? So that means I think the air for at most funny. This image is big, so you can generally trust the location. Seismic data. It will only become a problem if the seismic. Did you get it here? Then in that case.
That's just say
For the ASF site, where would you show the
They switched it like 2 days ago from Vertex. I was using Vertex already, and we come in yesterday, and they said Vertex is going away. They switched it. Yeah, it was like looking at it. The area of interest. Yeah. Oh, okay. Yeah. Yeah. We'll click on this thing right there. Yeah.
Oh, okay.
Oh, yeah. Because it only goes. I think it's not bad. Yeah. The old one never showed it. Or you can
It's too bad it does not you allow it to type in the exact coordinates.
You don't want to go to the website. That will make it
Oh, yeah.
Everything is so sensitive.
So I guess thing you can do is find another map. Just make sure. Yeah, try to October. Okay, November 1st. Try to close there. Oh, I see. So you have to limit your area and put it in there. Right. But is it easy?
Yeah.
That's the only thing I need from that.
Right.
I think it's working for my house.
So here's when I go right down there, it's just one go directly. Only have 6 minutes. Yeah, I would imagine it's easy. They're small, but it's.
Oh, okay. Now it's do it.
Anyways, do that.
Oh, yeah, how it works. See the front end of here. So make sure the point is near whatever you want. So then you zoom in again. Clear that. It would be easier if you know the exact point. Yeah, I guess you can just have to do now that's your first step. What you do make sure it has more jobs than 20 days. So it's
Oh, nice.
Okay, so you get 12 images. So all you have to do is zoom into that image. See.
You have to be on.
Is this the 7.3? Oh, I'm sorry. Okay. Yes, the one that I took a picture from the screen just because this is pretty intense. So when I'm doing the SAR, this is some work that the Japanese did, but it could be but Rob did and it worked out. But, yeah. So,
Yeah. All of these might work. You will see, but one of them you see better because everything is kind of.
So, yeah, this is one of the frames. I didn't know that the frames they come with KML, but floating.
Oh, yeah.
But super handy. Right, SOC to GMP. It's like no need.
So I send whatever you select here is here. You have to choose either dollar or add in the part. I don't know. You have to choose I tried it before. I think I can also make 3 or 4. It depends on your overall expenses. Your using house. Yeah, you need one image before the earthquake, one image after the earthquake. You start out with I think you can if this is a silly block. Okay, then I think over here you can this part only show up arrow is so up and down it's not that one this one's from okay, so in that case, you don't need to download the buffer of the buffer. probably depend on how topography. Yeah, the photo will figure it out.
Oh, that's good. Yeah. you can use that.
Two that are exactly the same, there's only a year.
But this is what it is.
Single figure.
Yeah. Go down to
I think this was one time.
Yeah, every time we change this, we have to go back to this. Have you logged in? You logged in. So it's
Just same thing on radar. Just kill that window.
Rob, you know how there's so he added images. Art. These two are probably or you have to figure out
I was just going to see that one.
No.
So this is 12 November.
Oh, you are.
Yeah, sorry.
So I use events. So these are the events.
Oh, yeah.
Yep. 1107.
Oh, it's usually not crazy for that.
Okay, so you use it for one. The 1111 is not going to work. You know, which your vote was 19. Oh, okay, yeah, okay, yeah, right, yeah. Well, I think they covered you there. I think I used
So you have, what's the name of the one? Canyon. Oh,
Yes, the water levels change.
November 7th.
I got the 11 and the 7 for the 17th.
Yep.
It's better if we use slightly different. Mine is gonna overlap with the edge of the east, and yours is gonna overlap on the edge of the west. Oh, so stuff like that.
Okay. And actually,
Yeah.
so that's, and then you have to download any data. Save file. Okay. So it's a lot faster. Yeah. So when you get those, in there, there's and the previous frame is more. Yeah, it's in the dot save folder. And then you have to yeah, then you run it.
Okay, that's exciting. It's not gonna work because it's only one.
Yeah.
Yeah, it's more so.
Is anybody having trouble getting a DEM? You're all having trouble. Okay.
Took a while.
Because that site is like down or overwhelmed. So why don't we do, if you can write the coordinates on a little sticky,
Oh, just. Oh, you want to do the download? Oh, you just click on another one. It will open. Yeah.
okay, we need give me the coordinates, make it bigger than the area. At least should cover the area of the.
Don't still around. Don't still around. All the time. Yeah, no, I mean, once I walk in, I'm like,
Oh, you have to start right there. Then you want to pick the Yeah, look, it's from yes, but there's still from one. Master of
The first one has the.
Yeah.
I'll be sent, you know.
So you have to run this
And
organized.
then you have this one that is let's just say, so let's say this is and then I have this other one. So then now I want I'll show you. I'll show you a refresh. So if you go to F1, that's what Bob says. It's a PDF viewer for no, this is one subframe. This is F1.
So it's not.
They're actually.
Another same.
What's the PDF tracker? Oh, the PDF didn't work. So we get F1, F2, and F3. But this is still one frame. Yes. If you go to the raw directory, there are only two sets. But these are the frames. This is what you download. It's that each frame has to be so it's not just maybe I'm wrong. Less is more, but with you can do page down and page up.
Yeah. It can be bigger than
I don't know.
So each one of those are subspace of the frame. And so it's going to keep creating a interferogram for each one.
So how?
So
We were talking like how would you face multiple frames?
So I think the latest,
But you won't be able to get it, Eric. You have to leave.
the latest PC actually like the
Oh, but it's marching still F1 and F1.
correct.
Yeah, so it's still one frame.
Yeah, it doesn't change.
But if I download then the next frame that is maybe
No, when you download a data, download a data file, it includes those three.
exactly so let's say that I downloaded this guy,
Right.
and that has 3 subframes.
Right.
But now I want to look at the next
Oh,
orbit and get and do another inter. So if it's a larger
Well, okay.
like an 8 or something
so
like
the
that.
problem there is they go to different dates. And so typically,
Oh, I get it.
you don't really, I mean, typically I don't combine interferograms from different tracks to different dates.
But if it's like a Mach 8.5, that might the fall might be 400 kilometers.
Yeah, so you
something like
can,
that.
but I mean, you'll probably get offset tracks somehow. Now, they probably will overlap a little bit.
We have to do GMT magic there to kind of like blend the
Yeah, well, or I mean, you have to think about what signal it is, whether you want to blend it. So then you might have slightly different discrete effects.
for what we did for California.
Yeah,
In there, that was definitely.
But yeah, right. So you,
So it's doable, but it doesn't come straight out of the box.
Well, he's-
Oh, yeah. From the window.
I don't think so. I mean, he's looking at slower range, so it's easier to overlap stuff. I mean, if you do a stack of say 50 of them, then your atmospheric is going to cancel out. You'll be looking at that. If you're just doing separate, anyway, you can. But I would be careful. That's going to contain. Well, it's raw data. Well, no, so I take that back. Sorry, it's SLC. I don't know. I've only ever.
The first one. Yes.
So yeah. Good. I mean, we're surfing now, right? Good.
Yes.
Works.
Yeah. So I grabbed November 11, 1500, 2017. It's the hour, just because we want to make sure it's the hours before the events. And then the other one is November 17,
You convert it to here.
1400.
Which one is that one?
And this is the second frame.
Okay.
For these two are same as yours. So we get the same.
So now how do you unwrap the face and invert for technique moment?
There's an option on here. Yeah. Just right change your paper.
Oh, there you go. Hyphen or just one hyphen?
Two. And then there's the APU abstract that automatically submits the order. In the summer of section of the interferogram over exit over
That's awesome.
So let us see your topography.
My topo directory. So I untar it. So it makes a file.
Where are you seeing that file? In my case,
Do you have FTP installed? Because I can push it to my FTP and you can just download it.
I don't have that ability. It's not in my case.
Do you have Firefox? Just get Firefox.
save this file. Oh.
Safari was logging. So
that means that I want to
make a bookmark for this guy. I'm gonna throw this guy. Oh, you already have it there. Yeah. Oh, because when we're in the at the board, you have this up there. Download it. Yeah, but the mission is when you have to get out of time. Yeah, where I cannot even push it. Oh, there's another one.
He used to give me one.
Yeah, but that was his site here. That was your account. And we have an account for you there. So I cannot even download it. So it's not.
Yeah, sure.
You have to time out. All right. I'm gonna have to go outside. The internet here is bad. The topography, yeah. 70 minutes.
Well, the big the higher floors.
The people are outside, and I can just either on the phone. Yeah.
I can't answer that question. They have.
CD time. Second burning a CD.
Oh, it just says like, oh, this is fine. This is one page.
Okay. I hate to interrupt everyone while they're working, but we should move on to this discussion of filtering and 2D phase unwrapping. And just before that, I'm going to give you guys this memory stick with DEMs on it. So pass it to.
How much 4x43 is the maximum. All right.
You know what to call them. So I'm going to give you a memory stick. Copy the one that and then and you don't have to unpack.
48.
Yeah.
Close to 48.
Yeah,
Yeah.
right now, my ear perception is right.
Yeah.
So it's
Back.
and I have 6 members that I see.
I've done these. We can start doing.
It's fun because it's fun. So,
You actually made a video.
Oh, SRTM1 is too small. So do SRTM2.
Did it actually work? Well, it's in the cost. Well, we're doing it like film.
I don't know.
So do you want to get started? Yeah, did it work? What's that? Where's the website? Go to the website again, or press the little circle. It'll enter it. Okay, so we're going to talk about filtering and phase unwrapping, and these are issues that you'll get to pretty soon when you start processing your data and it doesn't look quite right and you want to fix it up. So
I'll see if it's PDF as well.
oh yeah, we'll make it a PDF. Good idea. Is it
Right.
number 8? Yeah. Save as. Yeah, oops.
Save it to,
Desktop. Yeah.
it's not, it's you're saving
yeah.
to the PPT.
You guys have
Okay, for you online folks, we're going to start with a presentation on filtering and phase unwrapping. Matt Way is here to talk about this, and I guess we just preview, view, slideshow. Okay.
All right. Okay, good morning. If you click slideshow, it will move automatically. I'll just do full screen. All right, my name is Matt Way. I'm at University of Rhode Island. As I said yesterday, I did my PhD with 15 years ago, getting involved in some of the coding before it became GMTSAR. So I will talk about some about phase unwrapping. I try to keep it simple. Sorry to interrupting, but it will help you later on when you look at your data, right? And the notes are, I took some notes from other people for this. Okay, so once you did all your, finish all your processing, then you look at your folder, it's like this. Okay, that's what you will have in the INTF folder. There are a lot of files, but really what you really need is these 6. Okay, these are all PNG files. Okay, so you can quickly check your results by just looking at these, and you can look at the name. If the name is kind of indicating what exactly this file is. So there are phase, unwrapped, the LOS, and their correlation amplitude. I'll explain it more detail, but these are really the thing you need to look at. All right, so to link these files, really what we do is we get a phase in radar coordinates first, right? And then we do a geocoding to convert it to in latitude longitude. This is what you have.
And then what you do, we also use correlation to mask out places where, like in the water or something, that low correlation. So you see here, there's no colors because it's masked out. All right, this is geocoded masked out, and you can see the name is mask and LL. And then what we do, usually we filter it to reduce noise. All right, and that's your filtered one. Then you do an unwrapping. Okay. So unwrap the phase is, the units is still in radians. You want to convert that to like meters or centimeter. Then you do another scaling to change it to deformation, right? So that's basically the process. But the end member, this is what you need, the LOS, LL, that's your deformation map, right? And we'll focus on the unwrap part because that's an important place where might introduce noise or uncertainty in your image. Okay, first, why do we do the phase unwrapping? Because SAR measure phase change, not deformation. Okay, phase change is related to deformation, but it's not. Okay, so we have to convert this phase change to deformation. So that's what this unwrapping is doing. Okay, so this is one example from Airborne. It's in April 2017. It's a magnitude 6.1 earthquake. In the bottom, these are one of these ascending, one is descending, and you see these rings because it's a thrust faulting. So it's the pattern looks like this, and these are the phase image. Then you want to convert this phase to unwrapped deformation, right? So this is a phase unwrapping process, and in the end, when you try to compare your model with the observation, you usually do that for these unwrapped line of sight deformation, right? Okay, so if you draw a line, for example, like over here or something, that's what you have, the blue line. Okay, so your image is a phase image between pi and minus pi. Okay, so what you want is this red line, which is continuous and also it's correct. However, when you do this phase unwrapping, you actually get this green line. Then you have to, there is a constant shift for the entire image. So remember, anytime you have this kind of image, you can shift this entire image up and down. Okay, so InSAR is good at observe relative deformation in some way. Not absolute. You have to kind of assuming where zero is to make it right. Right. Okay. Our unwrapping is not always easy or fast. Okay, this is one case it's just not working. All right, this is a no, it's not unwrap. But unwrapping this one will be very difficult. Okay. Anyway.
Actually, that was unwrapped using a different algorithm that doesn't work very well.
So it's unwrapped.
It was supposed to be unwrapped.
Okay. Anyway, all right. Okay. So the ideal case is like just like this, where you have the blue line is your phase. Okay. Then once you unwrap, it will be the red line. All right. It's beautiful, continuous. That's the ideal case. But there are two problems with this. Any guess? So the real data doesn't look like this. What does it look like? There are two problems. Any guess? I mentioned one before. So one of the problems is noise. Okay. So in the red line, it's not like it. Usually there's more variation. Okay, that's noise. And the second thing is aliasing. Aliasing basically because the deformation is relatively large. It's beyond the 2 pi. Then you get some problem. I'll talk about these two. Okay. Yeah, noise and aliasing. Okay. So noise. Okay, so this line has a signal to noise ratio at 10. It's okay, right? But here is 2. And the red line is the noise, added noise to the signal. And here is 1. So you can imagine when you try to unwrap these, this one will be very difficult you have a lot of noise. Okay, that one will be very easy. Okay. So here is an example. This is Southern Sea. And this part looks okay, right? But when you get to the water and farmlands, you see these things are just very hard. Okay, when you I'll show later. Yeah, but this one is just to highlight the noise. You see, if you do any program, unwrapping program probably will do well here and here. But when you get into this region, it'll be very difficult. And so we need ways to reduce noise or try to get rid of the more. There are ways to make the unwrapping phase faster. Okay, so there are a few ways. Any suggestions? You can think of reduce the noise. What? Filter. Yes, that's one way. Stacking. Yeah, stacking. Other. Mask out. Yeah. Okay, I'll talk about mask out and the filter for this purpose. It's kind of the easiest thing to do. Stacking is a little tricky. All right. So the first thing is, okay, we can use the correlation map which we generated. It's one of the product that you will get. Okay. So the program, there's one thing that you can change to modify the threshold to mask out, but basically you want to mask out low correlation area and keep the area has high correlation. So over here, the correlation, white is good, black is bad, all right? So this is one of the mask out sessions. Here, the threshold is probably too low for this one. You get these mask out. But once you increase the threshold, you probably will mask out the entire place. You want to play with it if you're working on a tricky area because you do not want to mask out the region where you're interested. Okay, so sometimes it's a little tricky. If you're interested over here, then you can just increase the threshold to mask out this part. You'll be fine. But if your interest area is right here, you should be careful. Okay, all right. So when you look at your end product later, so any image has mask there. These are masked. All right. Okay. So this is your configuration file. Okay. And over here, there's one parameter called threshold SNAPHU. So that's the threshold you can play with about when you try to unwrap. So basically, any point have lower than this correlation threshold, SNAPHU won't try to unwrap it. And also, later on when you try to do the geocoding thing, you can also do this. This is just whatever image you get after unwrapping and also before unwrapping. This will mask out anything below that threshold and then convert and do the geocoding. This is really just a plotting thing, but this one is really for the unwrapping. All right. Okay, so you can also filter. So here's one example where this is probably the original face. Then here is a filtered one. And you can tell that the boundaries are much sharper in this filtered one. So it's easier for almost any unwrapping code to work with. All right. So for this one, can you tell which one is filtered? The right one, right? It's much cleaner. It removes all this high frequency noise. Okay, so that's what you can play with. In this product, there's one called face filter. So that's the image, filtered image. This one is the original case, not filtered. All right, so that's kind of, you can do a comparison later on when you get your results. Okay, so about filtering, we use Gaussian filter. And there's one thing you can play with, which is called filter wavelengths. So the default, I think, is that 200 meters for all. Is that right?
200 meters.
Yeah. You can it depends on your satellite as well as your particular case. If you feel like the filtering is too much or too small, you can change this to like 100 meter or 400 meters. See how that improves your image. Yeah. All right. So once you process everything, you want to redo this part. You don't have to start from scratch. In the script, there is a way you can define which step you want to back start with. So you can just back start with the one before this, and then you get everything later. Okay, so the second problem is aliasing. Let me see if this is easier to say. So basically, okay, so the black line is original deformation. Okay, so the difference is the black line is really sharp, the square steep over here. So then the rapid phase, which is the blue line, that's the phase. The original phase is black. Blue is the wrap. Yeah. When you try to unwrap from the blue, you will get the red line actually. That's because I think because over here is too steep. Well, it doesn't look like so. I don't remember.
At the end of the red and black. Yeah.
Oh, I see. Yeah. So all these parts they are relatively sharp. When you do the unwrapping, you are not going to, because it's just because the deformation rate is more than 2 pi. So you get more than 2 pi deformation within one cycle.
Yeah. So the unwrapping algorithm jumps bigger than something specific amount.
Right. Right. So okay, another way to think about this is when you try to do unwrapping, so you can assume there's, let's see, this table. You always assume point here is continuous here. So you are linking this. But if your real deformation is actually there's a 2 pi difference between this point and this point, and you won't get the correct unwrap phase. It only happens when your deformation is really large in a short distance. Okay. Okay, there's some data. I'll just describe it here. Okay, so this is the InSAR image from the Golkar earthquake in 2015 near Nepal. It's a really large 7.8, and create so this is image. And I forgot if this is modified or not. Is this the original phase? Does it look right?
That looks like a model on the right.
So what happens is, for example, over here you'll see a few fringes, right? If you assume assume these fringes are continuous, you will get a unwrapped phase. Okay. But what if the deformation rate is much higher, where actually you get 2 pi jump between these two fringes? And that's what the real, if you have a very large deformation, this would the real fringe look like if you reduce the wavelengths, assuming you have a smaller wavelength satellite. There's so many fringes. So basically, if you think from this blue to green, it's 2 pi, it's continuous, it's a 2 pi jump, but actually the deformation could be 4 pi jump. So you will underestimate the deformation field if that's the case. So it's rare, but once it happens, what you can do is you can build a model, then create some synthetic InSAR image, then subtract that model from this, then do your unwrapping. In that case, you will get rid of this steeper slope thing. Okay. But usually you have to do it many times to get it right.
Say that again. You computed the model that InSAR uses, right? And you did it in A, and then you are saying that you will subtract that outcome here.
Yes.
But this one is very uniform. Looks like the calculation one very nice. The rest, when you subtract it, what you subtract system then.
Well, so let me think exactly what we do here. Okay, we draw.
It should work if it's close enough. If it's close enough, it should work.
Okay,
If your model is sufficiently close to your gram, it should reduce the AOE. Remember, but you're going to subtract it in complex.
yes.
You're not gonna subtract the unwrapped part. You're gonna subtract it in complex, right?
Yeah.
Yeah. So you don't have to worry about matching up with little fringes. The idea is to make the model sufficiently close.
You
That
subtract A or complex.
you do it in complex.
But ambiguous and A together.
Pardon?
Ambiguous.
Right. Because in the complex realm, you don't have to worry about the fringes.
Okay.
So if you think about, so let's say the true deformation is this steep. Okay, this is the distance in pixels. And this is a true deformation. It's very steep, right? So if InSAR look at this, it will assume it's going this way. Let's see. Then when you unwrap, what you get is something like this. So there is a difference here. You have a contour. Then what you do is you build a model, assuming it has this steep or close. Then you remove that model phase or complex. Then you bring down the signal to like over here.
Then you read the way.
Then you unwrap it. Then you add the model back. So you get the entire thing.
Is it better? I mean,
Yeah.
You add that.
But again, this only is a problem when your deformation field is really steep or so large in shorter distance.
And to get to that, you are going to use just a point source.
Whatever your best.
Yeah.
model is.
Yeah.
What do you
You have to do it.
Okay. This is more.
Typically, what you do is an iterative fashion.
Yeah.
Right. So you do a very basic, simple model. You unwrap a little bit more of the phase. And you make a better model. You do a little bit more.
And this one has what is your explain that?
This is just a demonstration. It's not really
Not yet.
right. But anyway, this is probably most of you won't need this. Okay, but filtering may be the best thing, and mask may be the best thing you should do. Okay, so we use SNAPHU to do the unwrapping. It's an algorithm from Stanford. They have a paper on this. I'm not going into details, but basically, you can think almost like a regression problem, where you have a lot of points. You try to fit it in a fashion that minimum a misfit or something. So this unwrapping problem, in some way, you can think like that way. So the algorithm itself has a way to measure how good your fitting, your unwrapped face is. You try to just find that. Okay. Right. And there are other algorithms out there which have their strengths and weakness, but we use SNAPHU. It looks fine. It works fine. Okay. So what if your image is challenging? You have a lot of area, low correlation, noise. What to do? Okay. So in this case, if you want to unwrap this thing with SNAPHU, it could take hours, even days. Okay. The problem is when SNAPHU try to unwrap this region, it becomes really slow because it has to do like many steps, many calculations to make sure you can find the optimal unwrap phase. Okay, so what you can do here is first you can increase your threshold in SNAPHU. SNAPHU will mask out every area that lower than that correlation. Then only unwrap the place where high resolution, so it's easier. Okay, high correlation. Okay, the second thing you can do is SNAPHU allow you to just focus on a small area. So in your code, you can actually
in your script, you can actually define the region where you want SNAPHU to unwrap. For example, if all you carry is over here, you can give the coordinates of this small region. SNAPHU will just unwrap that part. I'll show you how to do that later. And also there's another way called SNAPHU interpolate. I'll give you an example. That will speed up your unwrapping. Okay. All right. Or if you
Buy a better computer. I like that.
yeah. Yes. If you have a supercomputer, you don't have to worry about the timing thing. That's fine. Anyway, okay. So here is show you how to do that. So in SNAPHU, in a script, in your configure file, there's one thing called a threshold SNAPHU. Okay. So if the place you work on is very challenging, a lot of low correlation place, you can increase this. So SNAPHU will only unwrap area with high correlation. It's easier usually, it's very fast. Or over here, this is in radar coordinates. So you kind of have to go to your phase.png, try to figure out the radar coordinates for your region, then put it here. So our code will only unwrap that part, then do the geo coordinates converting. All right. So how do you find the region you want? Okay, this is the phase in let you launch it. When you open the phase.pdf file in your INTF folder, you will see something like this, where x-axis is range, y is azimuth. So, for example, in this image, let's say if all I want is over here, I just count, okay, this is, I don't know, maybe 2,000 to 8,000 in range, and the azimuth is 4,000 to 6,000. And I put that in that configure file. So SNAPHU will only unwrap this part. It'll be very fast. Of course, your final results will all be just this small region. So you only do this when your research area is only a very small region, or not the entire image. If you're working on a large earthquake like 7.3, you don't want to do this because the deformation field could be as large as the image. All right, so these are little tricks you can do. So here's an example. So that's the original phase. If you unwrap that, it takes 6 hours for this case because it's really challenging. But if you interpolate, I think this, yeah. The way it does is fill in all these small areas. So remember this is high noise. And here, hey Dave, do you remember what this is doing?
Is that the near neighbor?
Near neighbor, oh, I see, okay. So what it does is basically for noisy area, it's kind of smooths out by using some certain algorithms. Where if you look at here, yeah, this is really a lot of random stuff. And over here, it's much better. It almost looks like some kind of filtering. But anyway, so this will simplify the unwrapping. So SNAPHU can do this in 6 minutes instead of 6 hours. However, okay, this is near neighbor interpolation. Okay. However, your result should be the same for the 6 hours versus 6 minutes. Okay. So what I mean is this one should be identical to this, or as close as possible. Otherwise, you might cause some problem in this interpolation process. All right. Just a couple other points. So if you have a time series, you might need to do 3D unwrapping. So not only just one image, you unwrap the entire thing, but also a long time. That's a little tricky. But this is one problem. Yeah, Scott Baker told me yesterday he saw a PhD advertisement, PhD opening in University of Leeds. So they are using deep learning to unwrap face. Okay, so it's closed, so somebody already got a job, but got a position. But maybe in a few years later, they use a deep learning or AI or whatever, machine learning, to develop
additional or a new method, maybe faster than SNAPHU. I don't know. So then we might adopt this as well. You know?
The other thing would be time series, unwrap a time series as well as a single phase.
Yeah.
That
Might be better.
it makes it like a 3D.
Yeah, 3D unwrapping. I mean, I have played with machine learning a little bit. I think it might be good for certain.
It's good at interpolation.
Yeah, it's good for certain cases, but if the area is as challenging as these, I don't think machine learning can do anything better than SNAPHU. That's just my opinion. It's probably faster though. Okay. All right. So after unwrapping, you have to convert the unwrapped phase to displacement. All right. So what we do is, if this is unwrapped phase, you multiply by lambda, which is the wavelength of the satellite, and then divide by 4 pi. Okay. So that's how you convert. That's what we did for convert the unwrapped phase to line of sight displacement. All right. So for Sentinel, it's 5 centimeter wavelengths. Okay. So here is a question: Why is 4 pi instead of 2 pi? You know the answer, so yeah. What? Yeah. Okay. So it's a two-way travel time, right? So that's why we do 4 pi. So what you get is really just the distance change along line of sight, right? Okay. Sometimes as a user, I recommend you to look at the wrapped phase first, because you might get the units wrong in wrapped phase. So for example, here, okay, this is the original phase. This is unwrapped phase. There's something wrong with this image. Did you notice? Not the image itself, but the label.
I think that's my image now. I see what's wrong.
Yeah. You see anything wrong?
In the scale bar, right?
It's in the scale bar. Anyone?
Maybe centimeter? No.
Okay.
Yep.
All right. So the trick. So you can almost count how much deformation by just counting the rings. So remember, every 2 pi is half wavelength, or 4 pi is 1 wavelength. So this is Sentinel is about 5 centimeter wavelengths. So anywhere from green to green should be 2.5 centimeter. Okay. So there are like 1, 2, 3, 4, maybe 4 rings from the center to the outside. Then you're talking about 10 centimeter, 7 centimeter deformation. So that's about right. So it's not millimeter, it's centimeter. Okay, so from the center here to there should be like 10 centimeter. Okay. So this is a true case where I had a postdoc who are new to InSAR, and he was inverting this with millimeter deformation. You know, so the final results are just wrong. Okay. Anyway.
How does SNAPHU decide to what center point to do the unwrapping out into this space?
That's a good question.
I think it's an optimization.
Yeah.
So I mean, it does the pixel by pixel unwrapping, but it treats it in optimization. It finds a metric, the optimal way, naturally change the cat metric. That if you're trying to unwrap the topography, the SNAPHU configuration file is different than if you're trying to use information. SNAPHU's got a lot of options on it.
Yeah, the nice thing about SNAPHU is it only adds or subtracts 2 and pi. And so when you're done and you unwrap the phase, and we do this all the time, if you take 3 SAR images and make 3 interferograms, like combining the 3 possibilities, when you sum that phase around the loop, it should be 0. But if if there's a phase unwrapping ambiguity, it'll be pi or 4 pi for the whole image. So it's always up or down, like you said in the beginning. It's always unknown.
At a given point, we have a plane of several points, right? So how does it, in which way it tries to first take 2 pi out?
I don't know how it gets started, but in the end, it's always off by 2m pi, and if you rewrap the phase, you get exactly what you expect. So that's a good thing.
Yeah. And again, for InSAR image, like the line of sight deformation, the entire image can shift any value. Okay, it doesn't matter. What matters is really the change from this point to this point. For example, if you know this point is 0, then you can ask me what's the deformation here. So when you try to produce a model to match the InSAR image, there is a constant value that you have to know, kind of estimate. Anyway, yeah. All right, that's all I have, I think. Any questions? All good? Okay, all right.
I think it's lunchtime.
I don't have it here. I have some of them here. But yeah, I need to do that. Yeah.
All right.
Yeah, I downloaded some of it. It's so slow here.
Could you do this in decimal? I can't do the degrees minutes.
It's not supposed to be about trusting.
Just decimal. Yeah, that's what. Yeah. Did that work for you? Did that, okay. Okay. So you unpacked it. Okay, yeah.
And I
Yes.
downloaded
ASM. Oh, it was on EM. Okay, cool. Yeah.
that's what I will try to model this route, this printers. Depending on where they use their epicenter.
Okay. Pass it around. So the whole thing is, you know, you put this in your profile directory, but if you don't want to use it, stand out with this weird. Because every time you run, your process is no, that's it's how it generates part of the beyond it.
Oh, you don't want to eliminate change.
So the way let's say this goes up by
No, I never tried it. What'll happen, I assume?
that's where that.
Yeah.
Actually, I don't know that.
So you see the real definition.
Yeah.
You know, SNAPHU can just do one
So these are the image. You only have one line.
Yeah, that's an important one.
So you mean like an type on there? I don't think it will because I don't think that's what part of the thing is like you can't do that. You do it too. You go around it and it plays right. So yeah, you go that same T the other direction, and you get a different answer. And if you get noise in phase, you make it an answer. You get the same thing. So that's actually a property of those rules.
So you have to give it in your INTF direction.
Yeah, that might be the sister comes in a whole.
And then you give it solar altitude elevation. And it returns a file.
Maybe later. You don't have to leave everything in that. There's a safe activity. Just leave it that way because the command takes that.
I just said it starts from unwrapping.
So
So you're going to have a file.
I'm just gonna copy that.
Yes.
That'll be your line.
Because the merge has this guy.
And you can run a full.
Yeah, we could.
And that will create a file. Longitude, latitude.
And both color outside. Yeah, there's
don't know why. How he actually does this. But, you could walk out and log with your yeah, you can make a file online and then you can add all that shit in. So you have long elevation. I don't know how yours does it.
That's why chapter. Here, like,
It's a SAR file. You have to make a new directory called topo, and you will start it there. But it's gonna make a new directory, and it's gonna put everything under it. What I did is I moved everything under the topo directory. I gave you a SAR file that just has topo. There's a download button that is going to show up, and then you click on download, and then it's going to be a dark code.
You can use the master. Oh yeah. So you have to do it. Yeah.
So that's starting in
Yeah, but site is broken. I think it's better.
So this threshold now is an area to be non-zero, right?
So file-wise,
I can do this on another.
Okay, no, zero would skip, right?
Here.
I think
if you put 0, it will just skip and wrap it entirely.
okay.
You have to give a number, non-zero number.
Make it a little bigger.
Yeah. But was there's an older number? Was it near interpolation? That if you set this number bigger?
Oh, yeah, that's the one I showed later. One means interpolation, others or back means. So if you want the
or not go fast. You will set it to not or just 0. What it will do is it will just bring the original phase to IRAP. To do the IRAP. But if
noise here, right?
not necessarily. It really depends on the if in your image, probably really, yeah, like this, no problem. I think you know,
No. Well,
so in this, yeah, I think it's set to 0. You don't really need it.
Do I have to run filter? Filter the unwrap interferogram?
No, all you care about is
someone gonna sign it?
what SNAPHU does is its own algorithm, which will recognize if you are reading the correlation line. So the code knows where.
So you give it a longitude.
Oh, I got there pretty fast.
You're doing more.
yeah, I did that email to people.
Oh, you got.
You might start making it fair today.
So here, this is not
What I usually do is
Yeah, you should do it.
the range the next one is 8.
Yeah, that's a good version.
Either one, master 6.
How are you?
Forgetting the
So your image is that. It's usually covered to you.
Yeah, I got a bunch. Yeah, it's the same. But this is like that you don't have.
Yeah. Anyone you want process, you need to all
Otherwise, you need to give you don't have to.
look at instructions. It should be somewhere. It's probably should be in the wall. Yeah,
Just make sure that
in the raw. Put the SBAS in the raw. That's kind of a fight.
okay, great. Don't want
Yeah, I think you just get better here. Oh. So I was. So someone told me that already I know. Yeah. Someone told me yeah.
down there.
Okay, I know.
He's trying to the base ratings. This is redoing something. For now, you can just run over later on, if you want to try all of the plans, it's only that higher. Specifically, so.
Yeah, those are like 40 minutes. Those are small.
No, you can't get 3 orbit until 3 weeks later. That's already not there yet. You can choose the rest, but then you need more camera. These orbits comes every few hours. So each for the hours or few hours. Then see that there's a time whether the you can make sure that this time period falls in our
Is that really money?
It's east of no. Okay.
So now I'm trying to.
That's pretty impressive.
From Mari. I have this.
So they define include this area. I don't know. And they can pose it by the
I'm doing the 5-minute facial wrap on there. Let me see if I can show you. I did a magnitude 7 on Pythagoras. That was from 2 years ago. But the only reason why I did it was that the halos so they did it, so I knew already that it was something that should work, right? If I do it right? Yeah, this is a different size, and a different but I'm trying to, okay, here you go, right?
we ran the whole thing.
Of course, I'm using different colors.
On historical.
Yeah, then I'm doing the face of wrapping. I'm actually I'm taking a picture with the phone. Yeah, I might take a round. Sorry. Yeah. Oh, there is. Of course. Right when you said. Yeah, but this, you can tell that this is a lower frequency because the fringes are further out. Yeah, that's the one. But this is a smaller wavelength, so the fringes come back quicker. So ALOS looks like it's a good data set. You have to have account. What's that? I'm redoing it with paper wrapping. Look at my fingers. See what happens. Okay. Not me. Yeah, he has such great sense of humor.
There's a couple of ways to
Okay, yeah.
Yeah, I know.
Most of the stuff we do is entry level LiDAR. Yeah, we need
Yeah, just a minute. Central projection. You call it or even better visualization. Same process.
Andrew's a product to make it easy now. But the Astro data, we have that's not normal. We have to give it to the GMT wizard. Oh, okay. How'd you guys do it now?
Back then, basically choose two lines. Go to the masters of the
Oh, yeah. Really? Yeah. Let's see if the GMT wizards, they have this online one.
you think
See if they can do it. Yeah. That's the program. Okay. We'll have to look at the output. These are data. Yeah. How many years? 2 years. Right. You guys have fun? Okay. If you can finish. Bring one here. Oh, yeah. Okay, I have a challenge. Make it easy.
Send a screenshot to Mark. So that's sure you're not thinking. I mean the visual day.
Depends on the.
So what is
Oh, yeah. Is there a sun out there?
Yeah, there's an ocean, there's a big old ocean out there.
Wow. Don't tell anybody.
Yeah. I have to take a picture of my daughter saying my life is about.
Picture of you eating one. Yeah.
Yeah.
Bringing that to your. I know. The meeting I have to go to right now.
bring this other box down to the 60 boxes here.
Are there 3 of them?
Yeah, there's 3 boxes.
wow.
I'm gonna bring this box up. Upstairs. Let me have one.
Paris, it broke the heat record by 40 degrees. Today. It's 105 there. 105. The record was yesterday. I'm sorry, the record was 104.8. So it didn't broke it.
Oh, wait. So
Sorry.
Yeah. Doesn't make a difference, or find out. Yeah. Kind of hard. Yeah. Especially when I think oh, okay. Large plane. Yes, we're sorry. Yeah.
Exactly, we were for yeah, I don't want space. Yeah. The only good thing I could deal with the that's the only problem. Yeah. Yeah, I would there. So where do you think we should substitute it? Oh, yeah. You drive like 12 straight, the meeting was like that. You can see, yes. It's like yeah. Yeah. So like when people
Something's running, so yeah, so I don't know if that Scripps will work for itself. Oh, you're right. It's a one. Oh, okay. All right. That's outside. Okay, so it might work. Yeah. We don't have rights. It looks really nice. I know it's going to be but I don't think you would want to do it. Yeah.
We're going to.
I think that's like the.
Yeah, I guess very different.
business is something. Follow map ways and recommendation of bypass here. Yeah, the only file that we have is BDM, but they come from the topics. So, yes. Well, those are the coordinates for this. Yeah. Not the skill area. So, can I see the targets?
People did not understand what I mean. He doesn't know that I mean.
It's great.
He knows me very serious. I didn't expect you.
It's very serious. It doesn't have a very good sense of I don't think our script works for us.
Did you run?
I didn't run. Yeah, just make them the download for you have to download file. That's what What is the smallest that this one can do? Medium confidence. What? 4.8? That's a good size. So you're gonna see maybe like 3. Shallow. Don't have any of those here. That's part of your No, I did not change it. I took it as is and it worked. Yeah.
Yeah, it's usually those complicated typos. Yeah, here I took a picture of the here. The cookie. Yeah, the cookie.
Yeah.
Andrews, they get you.
Oh, okay.
Yeah, it was funny. Somebody was throwing out old books in the library and they like poured coffee. Whatever. Yeah, I had to clean my bookshelf. But the other funny thing is the W guy. Afterwards, the reception today, I still use dog. I'm sure that made it happy or not. Really backwards.
You all are programming.
Yeah. Machine learning. Yeah. Machine learning all together in one program that figures out what you wanted to do.
Faster.
Yeah.
Programming language.
Yes. It didn't make sense to use errors.
Because it'll make it easy.
Yeah.
Sometimes you just want to talk to the and he just wants yeah. See why I got great and he just wants to and it's not what he's really we're trying to make the decision of getting on outside of remember in that second we're motivated to go around the rise of going around the city.
I would say to start in
Everything is expensive.
yeah, it is. I guess it depends on the class. We used to go to the start with my daughter, so. The big one actually, airplanes like
rest of it's like, when you go down, you see, it's really flat.
When I was in Korea, well, I had two.
One time I was talking to a friend of mine who was in a tradition as an attendant, where they actually had the ceremony or whatever. So I met him in the tree. But yeah, they're all
Well, actually, for submarine, there was a height limit. So if you're above that height, you can so I guess we both have heard it. If you're 4, 5, 5, 4, 5, 5.
probably, you know, you whack your head there.
Also, like,
I
mean, there's the sleeping quarter that makes its own of the dimension, so it's kind of pretty close there. Okay, face unwrapping on. Oh my God. Yeah. So this is the space filter and unwrap. There we go. It shouldn't be this easy. So it's still not a displacement at this point. Yeah.
It's like a movie.
Yeah, it's weird.
Vertically.
Well, it's not a vertical, it's flat.
Yeah, that's right.
So I think it's not last class. Yeah, so I think this is what I got the most. Well, you're seeing,
What's the reality?
Yeah, but it should have two color time. It's like I'm almost a deep.
well, I think it's more horizontal. It's really weird. It's, yeah, it's not a normal.
No, but I thought it was like perfectly reversed.
No,
Like,
I think it's more perfectly flat.
so this you think? I mean, at first, this almost looks like it's like the email has like maybe a
LOS, or that's just unwrapped, right?
so this is still not line of sight displacement.
It's well, it's line of sight phase, so it's recorded. So it's one eye. There should be something in there that.
So I copied it in my home. There's a unwrap LOL and unwrap It's almost nothing nasty.
Somewhere there's a man that goes from phase to line of sight.
So it would be LEOS, LOS,
yeah.
So is this going But this is sort of a sort of base.
The conversion from because you should have like a red But it's just going over it. What is the other one?
No, my approach.
There's another place.
It takes a long time. Trying to put it for application.
Yeah, like Scare's fun. Groundwater.
This ring is mine. It's no longer the It's pretty clean.
Groundwater. You saw the vertical one. You go to that
sitting there. Yeah. You want me to open that one?
Oh, no.
The semi-vertical. Yeah, so we're trying to remove the We use the model.
Oh.
Somebody's.
Oh, let me see if I can go.
No, I got 17. I didn't say you were. So, I also, I know what they're talking about. What's the resolution?
Where is this is from the beginning.
Okay.
Yeah.
Oh, yeah.
Okay.
It's a geocode.
You zoom in there. Turn off.
Yeah, it's just the Ukrainian I don't think it's a practical technology. This is a real error. I don't know what it is.
There it is right there.
Slash REL or slash bit.
So if I may,
This is an average. But there's you can run water things one of the ones that are
It sends us a lot of this.
That's going down.
I thought that.
well, apparently,
Yeah, I think I might have deleted a source function that was stupid of me. I should. There. I bad.
Yeah, I guess it's just. Anyways, he's asking about other areas, but it's everywhere.
Oh, if you want to see SNAPHU, it's there. SNAPHU is a directory called SNAPHU. And then there's a source there. Wow, Chandler, I don't know. What would that be? The thought should be created by it. Oh, Chandler, it could be a topography. It's outside of the brain. You might have to ask. I wonder if I don't think about what's not doing
This is going on. It's just the averaging.
$43, 46, 7, and then 33 and 4 to 36. You got 26. No, this is 46, 4. So my grid goes to 46, 7. And this is 40. So it goes all the way to the no, it's inside. Yeah, but maybe your son it includes this one. Mine is this, but maybe your friend looks that like that. Why you had that color scale? You changed it.
No, it's not my.
Oh, okay. Huh? Yeah, that's great. Oh, I don't have the face. Look how it came out. Oh. Yeah, so this is the first one. And now unwrapped. But it might be 8, but at least so you give the area of information. No, I think there's an issue with that it might have an alias, but it might be missing supply. So,
Well, I mean, I got it. That's part of
you have to make a special account. Oh, I think one. They all wrap. Yeah, 0. Let's see from 0. Or Fortran. Fortran is 1, 2.
Oh, it's here when you're. Why is it saying the build the wall?
Yes.
Okay, well, that's the,
Things, it exists already.
oh, I see. I thought it was,
Already able to. They have scripts on it. They have scripts already.
so if you look at Spanish, there's a macro email.
Yes.
If you can,
They
one is these, right? I don't try to do that fancy. So basically, one is the other is right. Yeah, so I'm just picking a set point. Plus or minus.
Only do it. Otherwise, how do it? The topography duration, or you will do that by default?
No, it's going to do.
It's gonna try to do it.
Everything. That's not easy to do.
So you do it at the end, you do a grid plot, function board.
Yeah. Because you know, it's processing patches and radar coordinates.
Okay. Because the grids are rectangular, but they're not rectangular.
Right, you're not lined up. Yeah.
But the longitude,
So it's
sorry, the latitude.
and also it's there used to be an option for just doing part of the interferogram divided by range. That's probably possible where you just start saying
why? So minus y.
if you're doing a really small area, something like that.
I need to learn what's going on behind the scenes. Like saving mistakes. It looked like something else happened here. It looked like the yeah, but I don't know if there was like a landslide or something here. It looks significant. It doesn't look like Oh, there looks like there's some. Yeah, there might be a lake there. But here, there's like another center there. I mean, you see that? This is like this I mean, obviously, this is the maximum operation. Oh, there you go. There you go. When you're doing like a presentation, and you want to call this, it will be like rectangular. So how do you do that? With a
What do you mean rectangular?
So when you want to make like a presentation, you want to make like in a slide, like you want to make like this, let's say.
You want to select a scenario prop, and screenshot it? What do you mean? You want to save an image?
Yeah, so if I want to basically maybe plot this GMT with another color map or something like that.
You have a grid file.
So I can do a grid code.
Yeah, GRD code and then GRD image, like what it calls.
This is a 7.2 in northwestern in the Iran-Iraq border. But I cheated because Rob did it already, so I knew that it would work. But when I did the face on Rabbit, he's afraid that I might be alias. I did Sentinel, and he did Halos, and he has like a red and blue pattern.
Really?
So
Maybe a different look angle.
No, he said that. He said that too.
Yeah. That looks like it would unwrap properly, from what I see.
It would be maybe good that like common error that happens when
Yeah.
so maybe have some example.
Unwrapping.
Yeah. So that.
Do you have a Google Drive here somewhere?
Yeah.
I want to open the PowerPoint.
Yeah, you can get it.
Mouse is not working.
Right at the water.
We'll just log in as me.
I think you can see this all there.
It's on the 19th.
PPT.
Yeah, PowerPoint.
Let's go to the top.
Number something. Yeah. Yeah.
That one there?
09.
Ah, where'd it go?
We could just use that. I mean, just double click.
Yeah, but you want to make it into a PDF because it
Oh, it's okay.
projects better
Oh, you mean for
for the projector. Ah, I download it. Download. Yeah,
it's not a photo.
make it into a PPT.
PDF.
Does anybody need any more DMs? Maybe it's small or something got cut off. What's that? I'll make it. Anybody else? DMs are okay?
Probably, but I like to.
Oh, nice. Okay, we're gonna begin the lecture again.
Yeah, let's get started.
Can you make sure that we're
Oh
talking
yeah, we
about
have to have the.
microphone?
So you can pull down the participants and see who's there. A few people are still hanging in. This is great. Thanks for hanging in there. You can send chat to Leo if you can't hear us or you don't get the questions or whatever. So we're going to talk a little bit about ScanSAR and TOPS, and then we'll talk about time series, I think, after that.
Yeah, after that.
Yeah. InSAR time series. Oh.
Oh, I see.
Okay.
Oh, yeah, I see.
Probably fine to put
Did
the
you
chat.
make a PDF?
Yeah, I made a PDF. So I put the chat window here. If any of you guys see a question popping up, please just remind me.
Oh, you got the chat window there. Great.
Yeah, okay. So next, we're going to talk about ScanSAR and TOPS, which is two wide observation mode for SAR. Okay, why I can't move? Okay, so why do we need ScanSAR? Yeah, we already have a beautiful street map functioning, sunlight observing the ground. Why do we need this ScanSAR technique? ScanSAR is just short for scanning synthetic optical radar. The reason we sort of want this technique is that it's pretty well illustrated by this PowerPoint here. So the smaller box over there is actually a footprint of a street map mode data from ALOS 1, I think, FBD mode. But you can see that immediately realize that ScanSAR covers a much larger area compared to this small frame over there. So in other words, there are a lot of situations like, for example, a really big earthquake happened. When you're trying to image it with this tiny little frame, you're going to need like tons of them to get a really good coverage. But for ScanSAR, you can easily capture the whole thing within one frame. So that's one of the biggest advantages why people want this technique. How does it work? We want it to be able to observe a larger area. So the engineers are developing this into a temporal complexing system. So it's dividing its observation period into small segments. Then for certain segments, we are observing this part of the ground. And then when you move to the next segment, you're observing a different place on the ground. Then you shift all the way to the end and then comes back. That's how it works. And the example of ScanSAR data is just the same. I mean, the data format is the same as a street map, and is no larger than a traditional street map data set. And because it's dividing it into different observation time, so you'll see that the first chunk of the data are actually coming from, for example, subsource 4. And then the next chunk of data is from subsource 5, and then 1 and 2 and 3, and then 4, 5. It's just that keeps in this kind of loop. But how are we going to deal with this type of data? If we don't want to write a new processor, actually, it's pretty easy. The way we do it is that we take out the piece that only belongs to one of the subsource, and then fill all the rest with zeros. And you pipe it through the SAR processor. It's going to give you a ScanSAR interferogram. So why does it work this way? But I mean, if you recall what was talked about this morning about the SAR image formation, while converting a raw data to a focused SLC, everything, including like deconvolving a chirp, or you're doing azimuthal compression, Fourier transform, all those stuff are linear. In other words, you are basically reading in the data, multiply it with some coefficient or fraction or something like that, and then add a lot of them together. So that's the basic procedure. So that's why if you just put everywhere else in this data set to 0, and it's still going to work for that subsource. It's an example of what you are going to get when you get a ScanSAR image processed. This data set is from ALOS 2. So you can see that this is a descending scene. So the satellite is flying along this direction, looking to its right. And that's subsource 1, 2, 3, 4, 5. Okay. But sometimes you're going to get this, especially for the very early data of ALOS 2 and ALOS 1 ScanSAR. Basically, it has nothing in it. So how did this happen? It turns out that this observation this observation mode kind of requires that when you are observing the ground in space, your orbit or that segment has to overlap enough. Otherwise, you won't be able to interfere. In other words, for example, what is plotted here is what we call a decreasing burst overlap, and that's the interferogram quality. Generally, when you like mismatching more and more on the ground, then your coherence is going to become less and less. And at a certain point, for example, like 0.2 coherence, you won't be able to get anything. So that's a really big issue for ALOS 2 ScanSAR, but luckily they get everything fixed in about like February 2015, right before the Nepal earthquake. So we are kind of lucky on that one. And this is an example of like not so good burst alignment. This is a Hokkaido pair, which is in northeast Japan. And this is a fringe or the interferogram after processing. But if you look inside the data, this is how they look like. These arrows, I mean, each of these chunk over here are actually what we call a set of radar bursts. So basically, over this period, you have radar signals coming in and reflecting. But also at other places, you also have some radar signals. Why is that? It's basically because you have both forward-looking and backward-looking. Even your strongest signal comes back right underneath your satellite. You still have, you're also observing the ones before and after your satellite. And we aligned some features based on the small like details over here. It's hard to see. It's only when you like magnify the image, you can find all these details. If you line up, for example, what is plotted here is actually a coastline. These two are matching together, but you see that the radar bursts are actually off by a little bit. And this kind of offset is going to cause a decrease in coherence and decrease your quality, the image quality. And later, there's a guy from JAXA that did this interesting thing that you find that the burst overlap actually changes in a sinusoidal way, like it has some kind of period. But luckily it's fixed. So now you can get this kind of nicely looking interferogram, except sometimes you have this kind of issues. So ScanSAR is really good in terms of covering a very wide area with not so good resolution, but it also brings us some problems. And one of the problems is that it's causing the target to be scattered. So how did this happen? If you remember what David drew when he's talking about the SAR theory, and we are observing constantly, you're actually having a Fraunhofer diffraction. You have a beautiful sync function on the other end. But when you are dividing that observing slit into smaller slits, you're going to, I mean, those observations between those small slits are going to interfere with each other. This is what you get from like high school physics experiment. Those kind of bars you're getting on the scene. And the more slits you're having, the scattered targets are going to be more obvious. So that's how, like in a straight map, when you look at two corner reflectors, they are really just two corner reflectors. But when you look at it in the ScanSAR scene, it's just a bunch of scattered targets. So that's giving us some problem in doing like image correlation. When you are matching two images together, sometimes you're matching this peak to that peak, and that is no good. So that's why at this end of this, for example, subsource 3, when the coherence is not so good, it's easily to cause this kind of problem. Also, another not so good part about ScanSAR is that because you are observing at one period, and then another period, and another period, your amplitude along the track is not very stable. So the amplitude, has an effect is what we call the amplitude scalloping effect. So it becomes larger and smaller, larger and smaller. So that's another issue if somebody is interested in the amplitude image instead of the phase. So after ScanSAR, there's another new type of SAR, which is called TOPS-SAR. It's actually short for terrain observations with progressive scans. Actually, this name is also designed because in the old times, there are a technique called spotlight SAR, which means you tilt your satellite antenna toward the target. It's just like putting a spotlight onto a target that have a longer aperture. But for this situation, you don't want really a spotlight. You want it to be sweeping backward to forward to get a better coverage. Think it's actually just the reverse of spotlight. So the reverse of spot is TOPS. That's why you get this terrain observation with progressive scans name. The idea of this mode is pretty similar to ScanSAR, except instead of directly observing, it's actually sweeping or electronically steering its antenna from backward looking to forward looking. Then this amplitude scalloping effect is getting mitigated. It's getting smaller. So after it sweeps the first subswath and then goes to the second and the third, and then comes back to connect with the previous scan and sweep again. Just continues. That's why most of you guys, when you are downloading the TOPS data, after you overlay that on the Google Earth, you'll see that the end doesn't really, it's not a straight line, actually has a jump. That's actually the burst you're seeing. Okay, this is a little bit complicated, but if you think about the spectrogram of this data set, I'm drawing it by hand because I didn't find a proper image. If you are looking at a street map, and over here, the horizontal axis is a time, basically where you are on the track. And this is a spectral domain where you're looking in the data. So you do have forward looking and backward looking. So a single radar scan is just like this, right? You're observing something with positive Doppler in front of you. You're observing something with negative Doppler behind you because of the forward and backward looking. And when we look at ScanSAR, you see that some period is missing because it's observing other subswaths. So you see the spectrogram sort of looks like this kind of stripes, one after another, one after another. But when you look at TOPS, because it's steering from backward looking to forward looking, it's actually introducing an extra Doppler ramp. It's much larger than this the PRF, the post-repetition frequency. That is, goes beyond the Nyquist and wraps back, and comes to the top and wraps back. Actually, the introduced Doppler from the sweeping is 9 times as large as the Nyquist. So there's no way you can do anything to the data without removing this ramp. So that's why the first step of processing the TOPS data is to get rid of the ramp and then do the correlation or data shifting, resampling, those kind of stuff. Also, there's another problem with TOPS. That is because at some region, for example here, where it's connecting from forward-looking to backward-looking, the spectral over that region is very different from the previous and the past, previous and the next burst. So over here, if you're forward-looking, you have a positive Doppler, but if you're backward-looking, you have a negative Doppler, and they are off by like 4.5 kilohertz. Like I said, it wraps up 9 times, and the PRF is only like a tenth of that. So this separation of the spectrum makes this region really, really sensitive to azimuths of motion. In other words, if your correlation or how well you're matching the two images is not good enough, you have a jump in your phase.
Can you program that in the chirp so that it takes into account the different beams before you do the stacking?
The chirp?
Yeah.
The range chirp? The chirp mainly controls like a range sampling, not the azimuth sampling. Yeah. So if you're doing a correlation or matching those two images using a traditional cross correlation, this is probably what you are gonna get, because cross correlation is gonna give you like up to like 0.1 pixel precision. Then you have, like I said, you have jump from one burst to another, and the coherence between this like from one burst to another will have a really dark line here because it doesn't match very well at the burst. So luckily, when we get this TOPS data, they are also being able to control the orbit very well and provide us with very precise orbit files. There are estimates that says it's only like 3 to 2 centimeters cross track, and 5 meter along track accuracy on this orbit. So with this really precise orbit, what you can do is that, for example, for any given point on the ground, you can easily compute what the points range at azimuths in the reference and repeat orbit. In other words, you know exactly where this point is in the radar coordinates for the master image and the slave image. You could just easily difference those two and use those numbers to match the two images. Actually, it's getting much more precise than doing a cross correlation. So that's how we did a correlation for TOPS. And here is just a comparison. So for the old cross correlation, it's pretty crude estimate on range and azimuth offset. But for new geometric, it's getting much more precise. Again, you have the deramping and the re-ramping there to sort of deal with the sweeping issue. So after you do the purely with the orbit using a geometric alignment to do the correlation, this is how the face we're gonna look like. So you don't have any jumps anymore, and the dark lines are becoming much more not obvious. Sorry. This is just a circuit test, but it was supposed to be animation. Somehow the last one jumps up first. This is sort of telling you that the geometric correlation works really well. The phase closure, when you add computing interferogram from like a loop, actually comes back to 0. So in other words, it's not introducing any error to the processing. There are cases, especially in some low altitude, low latitude, sometimes you would have this, after the geometric correlation, you still have this burst offset. And there are speculations on like what's causing this. One of them is ionosphere is bending the beam. So you have this offset because geometrically you have no information about what the beam looks like, right? So after that, there's a second step that you can do is called enhanced spectral diversity. Remember that we have an equation at the very beginning when we are doing this deramping. Like your azimuth shift is related to the phase difference at this overlap region. So when you know sort of about this phase, you can derive the azimuth shift needed to remove this difference, right? So after that, you apply this further shift to your geometric correlation, and then this discontinuity is going to disappear. That's called enhanced spectral diversity. Oh, this problem is probably already fixed, so I'm not going to talk about it. So this processing chain is already built in GMTSAR. It's pretty automatic right now. You don't have to deal with these issues by yourself, unless you are really interested. So that's pretty much it about ScanSAR and TOPS. Any questions? No, this is the script when it's doing processing. So this first part is just decoding the orbit, doing geometric correlation, doing not EAP correction, it's early correction for early data. But you don't really have to do that anymore. This is running spectral diversity and applying the correction, and then writing out the files. Any questions?
So for the ridge crest example, that was on the Sentinel
Yeah.
data, the top level script in the README was P2P underscore S1 underscore tops underscore frame.
Yeah.
Is that very different than just the tops.csa?
So the tops one actually only does one swath, and it's pretty old script.
Oh, okay.
The other one is going to divide the data, into different subswaths, process them, and combine it into one frame and give you the final result.
So it's just good to keep using the
Yeah.
ridge crest tool. If we're
Yeah.
doing a new Sentinel project, just to copy the
Yeah.
config text file and the script.
Yeah. If you are really going into that interferogram or the ridge crest example, you see that there are like some
Yeah, you have
lines.
on the web, show that on the website.
Okay.
You can see where the ground moves,
Uh,
along the track.
how do I do this?
So it could be another way to measure ocean in the plane.
Uh,
Surface of the earth.
Files are too big. Need a faster speed.
It's coming. It's halfway there.
Oh, that bar is.
That part doesn't work.
It's gonna stop there. Yeah, if you're really careful looking into the interferogram, sometimes you're gonna see a seam, like a sort of.
I thought you had a plot of the seams.
A lot of
It's not
seam.
on the website.
It's on my Twitter.
What?
It's on the Twitter.
Twitter. Oh. Twitter.
So if you're careful looking, you see that there's a line over there, which sort of looks like a correlation error. Oh, sorry. Sort of looks like a correlation error, but actually it's not. It's because this earthquake is a lateral slip for the big one, and this side of the cross actually really moved.
Why don't you go to your Twitter? You can see it.
How to log in? I don't remember my password.
Yes, the line is your Twitter.
Are we gonna? I don't remember. Oh.
Yeah.
Oh, there we go. Yeah. Perfect. Better than I do. So if you do an enhanced spectral diversity, this is what you're gonna get for the earthquake. That's where the rupture is, and that side really moved. The color is sort of wrapped because it goes beyond like a pi when you are computing the phase.
How did it move? You move like this or
It's moved like that.
so it strikes the kind of
Yeah, it's a strike slitting. The track is going that way, so this part of yellow or redness means it's going that way. The blue means that. You see that there, it changes from like dark blue to suddenly to red. That's because it's just like phase. And this is the place where you're going to see a discontinuity in your interferogram. Any more questions? Okay. Do I need to show this example again? I thought you showed it yesterday, right?
I was just thinking if you showed them the first mismatch.
Oh, okay.
Because
And
it's not like there's anything wrong with the data. It's actually movement of the ground.
yeah. Actually, Yuri said that if you know that displacement, you can actually, if you know your sleep model, how the ground is deforming, you can actually apply that to your correction, the A.GRD, to do a better correction. Yeah, then that seam will be largely gone.
Or you could use it as some data points.
That's too sparse. Yeah. It's wrapped, yeah.
very quick question. You have two problems there, right? Those two movement solution of whatever those strike of those faults he was pointing out. It was not one is that one is 6.4 is like that, SNAPHU is slightly off in its strike direction. What it is off in its strike direction? How did you get those mechanisms out? Or is that from seismic?
Yeah. So the question is that how did this two focal mechanism, where did that come from? Is it from the interferogram? No, it's from USGS. Yeah.
And these are images included both the events inside it.
Yeah, they have the nodal plane solution. You just plotted with GMT.
But you said that the actual slit is 90 degrees off from the other.
Yeah. It's almost perpendicular in the field. If you look at the
So
tracks.
when the seismic data first came in, no one knew whether it was left lateral or right lateral for a little while. Until the aftershock.
All right. That's it?
Oh, yeah, yeah.
They were delayed by like 8 hours.
That's a long time ago.
Okay.
I wasn't here either, but I remember.
Okay, there's a question online says, is it possible to do enhanced spectral interferometry in GMTSAR? How it is possible? So the answer to that is that when you are doing, there's a script called align tops _ ESD .C shell. And when you are running that to register the image, there will be an output called DD phase, which is double difference phase at the overlap region. If you read in that phase, that's actually the spectral diversity solution you can use to derive how much horizontal, the along track deformation is, but only at the burst overlap. All right. Yes.
More questions? Or? Well,
Now we're going to learn batch
time
process.
series. Again, if anybody has issues with downloading data or their GMTSAR or DEMs, put your sticky up. Oh, you have your sticky up. Okay. And I'm making DEMs over here because the DEM generator's down. All right, so Katya is gonna, oh, do you have a different PowerPoint or is it the same one?
I just uploaded it to Google Drive.
Oh, perfect.
Yeah.
So Katya is working at JPL now and she uses a software called ICE. And it's sort of a competitive software. So we're hoping that she doesn't try to infiltrate, yes.
Try to convince you guys to try ICE instead.
Because ICE is actually really good.
There might be some subliminal
good.
messages in the.
ICE is good.
You have to watch for them.
But I feel like there has to be a bit of competition
It has to be.
to get it right. Is this down here 10 key?
There's a 2019. So
Okay.
the second one.
Okay.
Yeah.
And eventually ICE might take over. Who knows? Download anyway. Oh, it has viruses.
What? Of course, they're ICE. It automatically installs ICE on whatever computer you download it to.
Oh well.
Which is not easy. Installing
This is
ICE
not my.
is very difficult.
This is a loaner,
Oh,
so
it's not yours.
I'm safe.
Damn it.
Okay. Key right there.
It's open, yeah.
But I'm gonna oh, Keynote might be okay.
It's
We
fine.
haven't been able to get a full screen thing.
Oh.
You try it.
Oh, screen sharing has stopped because your external display has been disconnected. You're right, it does have viruses.
Yeah. When you did Keynote, it went away.
I don't know, I didn't touch. You walked away and it went away.
Oh.
No, here it is. Keynote's fine.
Can we just run it? What happened when you ran it?
I didn't run anything.
Your screen isn't sharing?
Yeah, and it's not up there either.
Oh. You know how to fix this? You use Keynote, right? You don't use Keynote?
I don't think it's Keynote. I think something is
Well, we haven't been able to
disconnected.
get PDF to work
Oh,
on PP PowerPoint.
it's
Is this
just
your
not doing
computer or is it the one that was
It's,
here before?
it's my old
It
computer.
was-
Okay.
Here you go.
Because the screen isn't being shared with the Zoom.
Oh, yes, I remember.
Oh.
No, that's right.
So
No,
it's trying to put like half the monitor here, half the monitor
no, put it
there.
over this way. And then click on that and then click on that. Yeah. Now it's shared.
Yeah.
But there's no.
But
It said that the external display was disconnected.
yeah,
So I thought maybe it was.
this is kind of finicky.
Is there a stuff on the cord?
Yeah.
Oh,
Is that?
Or is that the right cord? It seems.
I mean, but it was the same one.
Oh, it's over in the wall there. See, it's falling out.
Oh.
is that it?
Yeah, here we go.
Okay.
That's good.
Aha.
It was my fault. I stepped on the cord over there.
Okay.
You did it on
And
purpose.
I did have a
so-
The screen is shared. Okay.
to sabotage my presentation.
So you don't have to believe all.
The title of my presentation is GMTSAR batch processing. So I'm still being civil. I'm not talking about ICE yet. All right. So these are the people that whose images and whose contributions have made it into this presentation, and I'm grateful to them. I'm going to talk today about the batch processing in GMTSAR, and we're going to focus on Sentinel-1 because that's the awesome new thing that we should talk about. I'll talk about SBAS, which is the method, a popular, fast method for calculating InSAR time series. And I'll also talk about atmospheric correction for InSAR time series, which is built into the SBAS script in GMTSAR, so it's going to be useful for you. So why would we want to do any batch processing at all? So sometimes you just want to make one interferogram, like when an earthquake happens, you want to make your ridge crest interferogram and then you're done. But many times you want to actually observe something for a long time. So such as volcanoes or even faults, what they do when there are no earthquakes happening. And there are many, many different applications like glaciers and urban stuff and hydrology and all sorts of things. So the most important thing for batch processing is that you have to create a stack of images that are all aligned to each other. Otherwise, you're going to have problems later on. So usually what you do is you choose an image that's called the master image. And they're laughing because they know how much I hate this terminology, because there is no problem with the first image being called the master image. The problem is that the rest of them are called slaves. So the rest are called the slave SLC, single and complex images. This is very sinister, so you won't forget it. Okay. Anyway, we have to align the slaves to the master. That's why they're slaves. All right. So anyway, so this is your general procedure for batch processing. First, you have to organize all your data and you have to decide on your processing strategies. You have to choose your master image, the evil looking red over there. And then you have to align, you have to force your slave images to fit the master image. And then you form your interferograms. And then you post-process, you do whatever other things you want to do with it. So there are examples for this available on the GMTSAR website from NVSAT and Sentinel-1 and probably more and more now than last year. So step 0 is organizing your data. And this is what your data is going to look like once you're done making your interferograms, or sorry, once you're, well, yes, this is, you're organizing your data. So for Sentinel-1, which is what we're going to focus on, you're going to have, this is a suggested structure that you might want to use. So you're going to store everything inside a folder with a track number, because everything for one track is going to get aligned. And you'll have a DEM in your topo directory, which is, you guys all have made DEMs by now. You're going to have your raw data somewhere. And then you're going to have the 3 subswats. Eric talked about 3 subswats, and they're going to be called F1, F2, and F3. And each one of them is going to have bits and pieces of this raw data in it for each subswat. And then each one is going to have an output folder with interferograms. And so what you're going to do is, well, you're going to choose your master image, and you're going to let your scripts know which master image you want to process. And so the script you're going to use is pre-proc-batch-tops.csh. And it has some required inputs. One of them is the list of data that you want to process, your DEM, and your mode. What was the mode? We used to have a mode. Is this not true anymore? What was the mode? Oh, that's right. That's right. That's right. You're right. Okay, yeah, I remember. So I've been using too much ice, guys. Sorry. So right. So if you I promise not to talk about ice, but I can't help it. So if you choose mode 1, what it's going to do is it's going to kind of create a compilation of your data. It's going to kind of do some preliminary processing. It's going to figure out where your satellite is in relation from one pass to the next, and it's going to make a plot for you so you can choose your master. And I'll show you a plot like that in a second. Yeah, it's called a baseline time plot. And then you can decide your master images and strategies and things like that, and which interferograms you want to make. So the input for the data.in, these Sentinel file names, they're really super long, so I couldn't actually fit them all in one screen. But this is approximately what they look like. They say something like S1A or S1B in the beginning. They have a bunch of letters. Eventually, somewhere there, they tell you the date and the time at which the image was taken. So the point is that to make this data.in, you have to say one image, colon, the next image, and then the relevant orbit files that go along with it. So after you run your pre-proc batch in that first mode, you will get something like this. So this is basically took your images and it calculated, and your orbits, and it calculated something called baselines. And the baseline, something that used to matter a lot, and now it doesn't matter so much anymore because baselines used to be big. So between one pass and the other pass, the orbital control of satellites wasn't that good. So between one pass and another pass, the satellite could actually be far away from its original position. But now it's not so much true anymore, but we still make these plots. So on the bottom axis here, you have the year in this example, and on the top axis, you have the baseline. And this is in meters. So for these 3 images, all 3 of them, the satellite passes within 50 meters in a 15-meter tube, approximately. That's really quite good. And when you look at these, they have kind of confusing file names over there, but these are the dates. It tells you the dates. And from these, you could choose your master image. How do you do that?
Actually, one quick question.
Yes.
From your previous slide, the Sentinel files, they were raw files, they were not SLC files.
Right. The question is, from the previous slide, thank you, Eric, were they raw files or SLC files? They were raw files. Yes, sorry about that.
Well, no.
What?
They were level 1.
Oh, they're SLC.
Yeah, they're SLC.
Because when you download from Sentinel, they
were already focused.
They're already focused, but these are downloaded from Sentinel, from ESA. So they're raw. We haven't made them into our own SLCs yet. Yes, they're still SLC format, but they're not aligned to each other. We haven't aligned them.
I think in the name is there a dot save.
Yes, that's right, because the EOF are the orbital files.
I think there's a dot save variant.
So for these ones, there won't be a dot save, right?
Okay.
These ones are what's inside. The safe is like a folder, and it has a bunch of stuff in it. These are the what's inside the safe folder. Yeah. So these are just the base batch processing. Yes. You're welcome. Okay. Yes. Again. So then we have a bunch of we've made this plot, and the best way to choose your master, and again, this doesn't matter this much for newer satellites, but it matters for older ones. You usually want to choose the image that's kind of in the middle, that is kind of close baseline wise to the other images, because long baselines, big distances can cause some errors. So once you've made that choice, you have to run your pre-proc batch tops again, this time in mode 2. And before you do that, the whole reason you did this is to choose your master. And so what you do is you take your master, the line that describes your master image, and you move it over to the top of your data.in. And then you run everything in mode 2. And what this will do is it will align your SLCs. Now you'll have aligned SLCs, not raw ones. And then they'll be kind of cut and aligned, and you'll be ready to make them into your interferometry pairs. Okay. So again, yeah, you've moved your master over to the top. And then you can choose the pairs you want to connect. And something interesting that you should think about is that interferograms that you can close in a circle, they should all add up to 0. This doesn't actually happen. It doesn't happen for various reasons. And this is interesting, but you know, to a point, you should get 0 closure. And if you don't get 0 closure, there may be something wrong. So step 3, finally, we make interferograms. So then you run this other script called intif.tops.csh. You give it a file called intif.in, and you give it a configuration file. In this configuration file, there's an example of it online, and there's an example of it in the GMTSAR folder in your distribution. And you can modify it in any way you want. And there's some important parameters you want to know about. One of them is the proc stage. It doesn't really matter if you're going from beginning to end, but if you want to reprocess, is this still true? All of it's still true, okay. If you want to reprocess any part of your batch, you can choose where to start. There is the master image. You need to tell it the correct master image. Don't lie, because it will know. Oh no. There's the threshold for SNAPHU. You guys heard about this earlier today. There's the filter wavelength. You heard about this too. There are decimation factors for range and azimuth, and another separate one. There's the switch length. Is it what? It's mask water now? Okay. It's a bad name. We used to call switch length the immigration parameter, but it's now called mask water. And you can, I think, what would you give it, true or false, or 1 or 0? 1 or 0. So you give it 1 or 0. If you give it a 1, then it will mask out all the water before it does any processing. This is helpful because you don't want to look at water when you're unwrapping or anything else. Defomax is an interesting parameter. I don't remember what you guys decided. So basically, it controls how you unwrap when you have big displacements. So normally, as you guys have heard today, when you have displacements on the ground that are over 2 pi, you can't, it becomes really hard to unwrap. So your algorithm breaks down. But you can tell your algorithm that displacements over 2 pi are allowed. And sometimes this helps you. So Defomax sets the maximum amount of deformation that you want to expect. And if you're looking at slow processes, if you don't expect anything real that's going to be over 2 pi, you set that number to 0, correct? Okay. All right. So finally, we make the interferograms after you've populated your config file. Oh yeah, and by the way, intif.in is a list of pairs that you want to create. So now you have a whole big bunch of, sorry? Yes. Defomax. Defomax, yeah. So that's, if you're observing slow processes, you set that to 0. The question was what was Defomax? And if you are observing something fast, you can set the maximum of real deformation that you can expect to see. This is for unwrapping. Because otherwise, if your deformation is really fast, your unwrapper will break, but you can tell it that it shouldn't break, and maybe that might help you. Or maybe not. Yes. So the units are radians, right? Yes. Units are number of cycles. Okay, that's it. Okay. So again, for intif.in, you have a list of pairs that you want to connect, and the names, these names, where you get them from, these are the output names of your SLCs. So you can form this intif.in file, and again, you can make a list of pairs by saying first date, colon, second date, and you make a big list of interferograms. Now, how do you choose which interferograms you want to make? Well, okay, I'll talk to you about that in a second. Before that, once you run your processing, batch processing, sometimes maybe you want to just process one subswath of Sentinel, since we're talking about Sentinel, and other times you might want to process more than one. You want to merge them all together for your final product. So in order to do that, you're going to have to set proc stage to 1 in your batch tops.config, and threshold SNAPHU to 0, and threshold geocode to 0. So you run it that way first. You run that first, and then after you're done with that, you will you can run merge unwrap geocode tops for individual interferograms, or batch merge.csh for a whole bunch of them, and that will give you merged interferograms. All right. So for other satellites, I'm going to mention this just very briefly. For Sentinel, this is what we do. For other satellites, things are a little bit more complicated, because as I told you, baselines used to be a big problem. Yeah, they used to be big. And so you couldn't align everything together just by choosing one master image. And so you had to go through this thinking exercise where you would choose not one, but several masters. And so you can, what you would do is you would choose several masters, and here in this little plot, they're marked as stars. They're all masters. And so basically you look at your baseline time plot and you identify areas that are kind of clumps where images are clumped together in baseline space. And then you choose a master in each clump. And the trick is that the master should not have a very long baseline with this other thing called the supermaster. So in this case, you have masters and a supermaster, and then the rest are your slave pairs. So the slave pairs will get aligned to each master, and each master will get aligned to the supermaster. This gets even more tangled and messed up than before. Yes. Yes, this is what you would do for things like ERS and NBSAT and other satellites like that. So once you're done, your interferograms are going to be stored in individual folders in INTIF or INTIF-all for Sentinel. They're going to be separate for each subswath unless you merge them. And each folder is going to be named after 2 dates. And the dates are year and then the day number in the year. And each interferogram will contain the following files. I think you guys already kind of talked about this. It'll have amplitude, phase, correlation, unwrapped phase, filtered phase, and all of them are GRD image files, as you know. And if you are interested in geocoded files, they're going to have a suffix LL, and PostScript plots, I think you guys are making PDFs now, right, are going to be .pdf or .ps, and there are some Google Earth files that will come out too. So let's see what happens when we have lots of interferograms, not just a few. So when we had just 3 images, we just created 3 interferograms in a loop. If you have lots of them, how do you decide which ones you want to make? So you have options. You can make sequential pairs, so you can just connect one to the next, to the next, to the next, to the next, and make those pairs. But maybe you don't want the little short ones, because the little short ones usually have a lot of noise and they don't have a whole lot of displacement. So maybe you want to make year-long ones. So you want to make long ones and then stack those, or do whatever you want to do with those. Or maybe if you're not picky and you have lots of time and space to waste, you can just make everything. This is up to you, and it's going to depend on your application, to be honest. So that leads us into what you want to do with your interferograms after you've made them. And this is going to lead you to decide how many of them or which ones you make. So first thing you can do with your interferograms is you could just stack them. So you can just make a bunch and average them all together and then look at the average rate. And that's great because that beats down the noise and you can just look at displacements. But it's not very exciting anymore because we have these sentinel acquisitions that are every 6 days, every 12 days, 24 days. And so we can look at much more exciting things that are changing quickly, processes that are that we can make time series for. So time series options, you could do SBAS time series. There's a test case that's available on the GMTSAR website. GMTSAR has a built-in script to do this. There's InSAR, persistent scatter. There are several different methods to do this. The most popular one here is stamps. And you also have the option of Giant, developed at JPL. I had to put in a plug for Giant. And it's got a bunch of different tools that you could play around with. It's in Python, if you like Python. So today I'm just going to talk to you about SBAS, that's all. So this is how it works, and this is a rather complicated chart, but it's actually, things are really not that complicated. So for, what it does is it creates a bunch of, you put together a bunch of matrices, and then you try from your collection of whatever interferograms you made, you try to get displacements, cumulative displacements through time. And so the way you do that is you define this design matrix where you have a bunch of ones and zeros. And the ones indicate the length of time through which the interferogram was acquired. So, for example, if these are months, if this axis are months, this is January, February, March, etc., then this first interferogram has 2 ones and then the rest are zeros. It means that it was acquired, the first image was January and the second image was February. So it's February, March, and so on. You can put other stuff in this matrix. For example, you can correct for the perpendicular baseline. Again, this is something that used to be important, not so important anymore. You would have certain errors that are associated with this, and now for Sentinel, it's not necessarily so important. You can add some sort of regularization or smoothing to it, to this inversion. So you have various options, but what you're solving for is incremental range change and eventually, so displacements and then eventually displacements through time. Yes. Yes.
And you have also used on the perpendicular baseline, and you can use
Oh, yeah, well, because, so, that's a long explanation. It has to do with, you know how you use your DEM, right? And if your satellite acquires, if your satellite were in exactly the same position, the question is why do we use perpendicular baselines here, for example? If your satellite acquires data in the exact same position each time, all you get in kind of the ideal world is displacement. If you move, then you have displacement plus some estimate of the shape of the Earth in that area. And that shape, that signal is proportional to the perpendicular baseline, strength of that signal to the perpendicular baseline of the satellite. So if what we do in this processing, as part of this processing, is we try to remove that. However, what if your DEM is wrong? So what if your DEM is off by, in some places, by some amount? You're going to not be able to correctly remove that from each interferogram. But the amount to which you're going to be wrong is still going to be proportional to the perpendicular baseline. And so you put that into your inversion in order to solve basically for the component of displacement that is always proportional to the perpendicular baseline, because you know that that's probably an error. There shouldn't be a reason why any deformation is proportional to the perpendicular baseline. So that's why we do this. Right.
One quick question.
Yes.
And
No, it's good. I like pain next.
you have those weighting factors, lambda and minus lambda.
Yes.
And always first starting to image has got lambda and other one has got minus lambda. What's the reason for that?
This is for smoothing. So this is a kind of sorry.
Like a boxcar.
It's sort of a differential. You're smoothing. You're enforcing the first derivative to always be as close to 0 as possible. So you're trying to smooth over the first derivative.
And what is the value that I use for lambda?
Sorry?
What is the value, the number that you use for lambda?
That's up to your discretion. Yes.
What decides that?
For example, a regular data set tends to number.
Okay, so the question was, I'm supposed to repeat the questions. The question was, what is the parameter? What is lambda, and what number should we use for lambda? And the answer is that in GMTSAR, the way that the inversion is set up, a number between 1 and 10 should be good.
So that is from experience. Basically, doing a lot of work, right? Go ahead.
This is something you have to play around with. You can run it and see, oh, it's too rough, or no, it's too smooth. Yes.
You haven't talked about that. Up here, you can probably do even smaller.
0.1 means rougher. So the smaller the lambda, the rougher your time series. And yes, it's true. So we're going to talk in a moment about atmospheric correction that reduces the scatter by a lot. So you might not need this lambda very much at all. Okay, but before atmospheric correction, there's one more thing I'd like to note to talk about. One thing that you could add to your inversion, to that big matrix of all this good stuff that you want to account for, is coherence. And you have some estimate of your coherence from your, for each interferogram, you have an estimate of coherence. So if you just do your SBAS traditionally, you get something like this. It's this image, this is a fault running through the image. One side is blue and one is red because it's moving in the opposite direction. But you see that there's a lot of scatter. You see it's pretty noisy. It turns out that a lot of the scatter is because coherence is not good in these images, and so they tend to be noisy in these particular pixels. However, if you basically put a constraint into your SBAS, which you have the option of doing, by saying, well, pixels with bad coherence should not be as important as pixels with good coherence, then you will basically have this coherence-based SBAS. You have a much smoother image. You downplay the importance of bad, noisy pixels. That's what you're doing. From a paper from college with 2016.
What journal is that?
Sorry?
What journal?
What journal is that? Remote sensing. We don't remember. Yes. Good questions. All right. So time series example. This is ALOS data over Coachella Valley. This is an old example, ALOS 1. And this is prepared with, the signals here are quite large, as you can see. So red is range decrease. That means red is uplift, I guess. Anyway, so this is prepared with the SBAS scripts that is included in GMTSAR. So you can see that there's a lot of motion going on in Coachella Valley because of farming, because of pumping of water, things like that. So some of the input that goes into the SBAS scripts, some of the basic input is your list of interferograms in interf.tab. You can see examples of all these inputs from the example on the GMTSAR website. So I'm not going to show them to you right now. There's a scene.tab list of scenes, There's the number of interferograms and the number of SAR scenes and the dimensions of the interferogram, the number of pixels in X and Y direction. And that last one should be the same for all the images. And again, don't lie to the script, it will know. So okay, before I move on, any questions? Because I'm going to move on to atmospheric correction. Any questions on basic time series? Yes? Yes. Unwrapped phase, yes, correct.
So for any individual unwrapped program, there's an unknown
Sorry, yes. Thank you. That is correct. So yeah, this is an important step. For any individual interferogram, there is an unknown constant because every interferogram is offset by some unknown amount based on where the unwrapper decides to start. And that amount is some factor of 2 pi. Yeah, so the way that we could deal with this prior to setting up this matrix and doing this inversion is if we choose a point in our interferograms, in all our interferograms, where we can say, just hypothetically, that we would expect or we can assume that the deformation is 0. Or a point, another way to think about this is a reference point relative to which we want to calculate our deformation. I mean, in some reference frame somewhere, the deformation is not 0 anywhere, but it's just a matter of what matters to you. You pick a point where everything else moves relative to it. So
choose that point in one pair, or you choose
in every single pair, you choose the same point, and you subtract everything else, all the other pixels from that point. Sometimes it can be a group of points. It can be a little area if you want. That's something to play around with. But that's what you would do prior to this, because otherwise, thank you. Otherwise, you can't look at time series, and you're going to have.
Another way to do it is to force each interferogram to match all the GPS differences over those times of relevant points. So you work at the interferogram match each GPS.
This,
if you have
GPS, yeah. If they're kind of evenly spread throughout, yeah, that's true. Yeah, you can do that. Yeah, good point. There is another way. There's a comment that there's another way you can try and if you've made a lot of interferograms and you've made a lot of loops, you can try to do an inversion to force every loop to close. However, the solution for that is non-unique, so it does not necessarily. The more offsets you have, the less likely you are actually to get an answer that you're looking for. So, this movie has to run. Sorry. There we go. Atmospheric correction. So the biggest issue that we have with InSAR is that the radar signal as it travels down to the Earth to measure the deformation that we want, travels through a lot of the atmosphere. And mostly the biggest culprits in our time series, especially at C-band with Sentinel, is the troposphere, is the water vapor that it encounters. And on your right, you see an image, and the color scale is between about 25 to 25 millimeters. This is quite big, but this image is very small. It's only over a time period of, first of all, it's not in an area that should be deforming, at least not in an area that was deforming prior to Ridgecrest. This is the Mojave Desert during the quiet years. And you don't expect any deformation here. I think this was an image that was over 24 days or so, or even less. And so you expect to see no deformation, and yet you see all this signal. And all this signal is really from, just from the atmospheric delay. So this is quite big. This is almost plus or minus 2.5 centimeters. This can drown out any kind of deformation signal that you might have. Probably not an earthquake, but anything you want to do time series with. So why does this happen? So we have radar waves that are refracted, their speed and their direction changes because of pressure differences, spatial pressure differences, temperature differences, and water vapor. Water vapor, again, being the biggest culprit. The problem is that tropospheric noise is unpredictable. It can happen at many different spatial scales. You cannot assume anything about the spatial distribution. It has a turbulent component that is uncorrelated in time mostly, but it's correlated in space. But there are also seasonal weather patterns that are correlated in time. And there are layers that will cause you to see a spatial correlation with topography. So it'll look like you're seeing topography in an image, even though it will be just a really strong atmospheric signal. So you can't really make an assumption, and you can say, I think this is what my atmosphere looks like. I think I'm going to get atmospheric signals at this precise wavelength, and I'm going to filter them out. That's not really possible. The ionosphere is a big deal too, especially for satellites that have longer wavelengths, such as, for example, ALOS and NISAR, which is coming up soon. What happens here is that the radar phase actually speeds up as it encounters these charged particles in the ionosphere. The good part is, though, is that the ionosphere is dispersive. And so that's very convenient. This means that shorter wavelengths travel at a different speed through the ionosphere than longer wavelengths. And so what you could potentially do, and what this group has been doing, and what our group at JPL has also been doing, is developing methods where you take your bandwidth of your satellite, and you take the wavelengths at the very edges, and you calculate the differences between what you see for these different wavelengths, and you can back out what the ionosphere might look like. This is not always completely reliable, but it's a big improvement. NISAR, by the way, is going to have going to operate at 2 different wavelengths, and that's going to help a lot with this issue. Yes, question? Okay.
So does the polarization is also affected along the path, or like if you have like
polarization, is it affected along the path?
Like if it's anisotropic?
I would think so, yeah. I would think so.
If you're doing cross-polarization, you could derive like a data product.
Probably. But I don't know. Yeah, it depends on I think it would depend on.
Rain, but I don't know if it will work for the ion.
Does it? I guess so. No?
I think it affects the polarization. There's something called Faraday rotation.
Yeah.
And that's how the polarization gets distorted, but I don't know if you can take that and invert for the ion.
We haven't tried that. So the idea, again, I'm supposed to repeat the questions. The idea is that does the ionosphere affect the polarization, and can you then make measurements at different polarizations and then use that to back out the ionosphere? I don't know. It's a good question. Anyway, that's something we can discuss.
If you have done the time series and that, you take for the same area one set of time series and then another set of time series, and do the things that come out the same result.
You mean, so the idea is you make 2 different sets of time series at different polarizations, and see if the results are the same.
In between time series, extreme tools the same.
This sounds like a research project that you may want to do. This could be a good PhD project.
He's looking for an internship.
Okay. I'll let them know. Okay. All right. So what do we do about the atmosphere that is such a huge pain in the neck? We can, the most obvious thing to do, this is what everybody says first. They say, well, why don't you use weather models? There's weather models all over the place. The weather people know what they're doing. Why don't you use those? Those actually don't turn out to work so well because their spatial resolution and their temporal resolution is not enough to be able to help us very much. It actually does help us. It can help us with seasonal patterns, seasonal weather patterns. But the turbulent component is usually wrong because the weather models are calculated with data that is from things that happen at a different time than the SAR acquisition, for example. And so that can introduce differences. Also, the spatial resolution is very, very different. It's much worse for these models. So that can be a problem. In the same vein, total electron content of the ionosphere. I apologize. We also have those models. It's the same issue. I think they're fairly accurate, but they're not very high resolution. They're very low resolution. Filtering in time and space or both. This is something that I've already mentioned. You can't really assume how your atmosphere, ionosphere, troposphere behaves in space or in time. Or topography correlated models, because as I mentioned, there are some, in some cases, when you have kind of atmospheric layering, it will look like you have a topographic signal in your interferogram when you actually don't, and that comes from the atmosphere. So you can calculate a correlation with topography and remove that. But these approaches actually also have some issues because, well, for the topography correlated models, what if your deformation is also correlated with topography? What if you're looking at a volcano that is supposed to inflate exactly at the center of the volcano? And you might remove that if you just do a topography correlated model. Nevertheless, it's useful. So in any case, I think that in my own personal opinion, this is not the opinion of JPL, I have to make a disclaimer, right? In my own personal opinion, the best way to deal with any of this is a combination of all of these approaches in some way. So, okay. So now you know about all of them. But I'll tell you about one more. So we developed a method here at Scripps with my former advisor who's sitting over there. He's never come to any of my talks at GMTSAR workshops before, so I'm rather flattered. That's Dr. Yuri Fialko. So we developed this method for atmospheric correction where we just rely on SAR data to tell us what the atmosphere looks like, because those signals are really big and strong, and you should be able to figure it out. And this especially works for kind of shorter interferograms that we have with Sentinel and such. And so the idea is that if you have 3 interferograms, like you see here, the blue, the red, and the blue points. Sorry, if you have 2 interferograms and they share a common scene in the middle, then if you were to take the phase from these interferograms and subtract it, you would amplify the atmospheric contribution. So because the 2 interferograms because they're just differences, right? So the first one is 2 minus 1, and the second one 3 minus 2. So 2 interferograms that share common scenes will share the same atmospheric contribution. If you subtract them, that will give you more atmosphere and less deformation. If deformation is linear in this time period, it will actually cancel out if your acquisition times are equal on both sides. And you will just be left with the atmosphere. And so if you do this for the entire catalog of interferograms, if you start from the beginning and just move through time, you can center yourself on each subsequent position, and you can look at interferograms on one side and on the other, and you can choose a certain number of them and subtract them from each other, and then you'll have the atmospheric contribution for that date. So the trick here, though, is that you want to choose, what you're assuming is that during that time period that you've chosen, where you've chosen the interferograms before and after, your deformation is approximately linear and your time spans are equal. And if that's not the case, you have to kind of deal with that in various ways. And so you can read more about this in our 2015 paper. There's more to this approach, actually. There are more details. It's a little bit more complicated than that. So again, yeah, I know my name is hard to spell. I should have probably made it bigger for those of you who are writing it down. Yes. So anyway, what you end up with is you end up with all of these for each acquisition date. You end up with an atmospheric phase map. And this is what all of them look like. This is again over the Mojave Desert, a bunch of tiny ones right here. This is over 20 years worth of ERS and NVSAT data. So we're going to look at some of them more closely. So these are atmospheric phase maps for these particular dates that I've chosen because they're interesting. These two are interesting because if you look at them carefully, they're basically inverted. And the patterns, however, are the same. And that's a sign that you're really looking at atmosphere because you have this correlation with topography, and you have these patterns that are unlikely to be deformation because they're just opposites of each other for no really good reason. And you have other ones. You have scenes that will have a lot of noise, and you will have scenes that are quiet. And so you can figure all of that out from the SAR data.
Do you try to constrain the hour of day to be similar, or it's not critical?
That's an interesting question. They are always taken at the same hour. So unless you have, for the same track, the acquisitions will be at the same time, always. Question though. So what we can do from there is we can estimate how bad each of these acquisitions is. And this is a plot, again, over 20 years, the ERS and NVSAT data, of good and bad scenes. And you can see the red are particularly noisy. These are normalized to have the highest value of 10 and the lowest value of 0. The absolute RMS measurements don't mean very much, but in any case, you can see that there are some dates that are quiet and some dates that are more noisy for whatever reason. So I just want to show you and prove to you that we think that this actually works and why we think this actually works. So first we did a bunch of synthetic tests. What you're looking at, these synthetic tests are here on the right side or the left side of you, the left side for you, yeah. And in each of these plots, the crosses, the black crosses, are uncorrected data that we haven't subjected to our correction. The blue is the original input deformation signal, and the red is what comes out after our correction. So these are pretty good. So on the very left side, on the far left side, panels A, B, and C, you have very regular acquisitions. You have very frequent acquisitions. And you can see that the signal is recovered very well. On the right is what happens when you have infrequent acquisitions, when you have data gaps. It actually, on the right, looks kind of a lot like this catalog. You have this big data gap in the middle. The signal is not recovered as well. So the red again is the recovered signal. It's kind of noisy, but it's still it's still an improvement over the black. And these signals are small. They're for the linear one, it's less than 1 millimeter a year. Turns out. The traditional small baseline are the black crosses without correction. Yeah, not bad. Because these are small signals, right? Blue is the input, and red is the recover. Sorry? They are SBAS inversions of synthetics. Because we didn't make sequential interferograms back then. I did not use any smoothing in any of this anywhere. Okay. So if you don't believe synthetics, I can also show you GPS. Comparisons with GPS, we did quite well here, I think. So in the blue, in each of these examples, so we chose a reference GPS station, CHLO, and we calculated differences because I told you, remember, that you need a reference point somewhere that you consider zero. So our reference was the CHLO station, and we calculated differences in displacements between it and 4 other stations here in the desert. And the blue in each plot is the GPS. The black is the uncorrected InSAR, and the red is the corrected InSAR. And you see that we can recover the motion from the GPS pretty well. There is even one plot in which, I'm sorry, I tell this story all the time, but I still love it. There's one plot in which InSAR actually wins over GPS. This is very exciting. It's the one with CHLO and CHMS. You can see that after the year 2005, the GPS starts going kind of crazy seasonally. And the InSAR, it follows the general trend, but it doesn't have the same crazy seasonal signal. And for a long time, everyone asked me why, and I told them I don't know, until I found out that, in fact, CHMS is a something middle school. And the middle school had a station, a GPS station right in its yard, and they decided that it was ugly. So they planted a tree right over it. And so year in and year out, you can see the tree shedding its leaves onto the station and creating these false seasonal signals that are not actually real signals. InSAR didn't care about this tree, so InSAR doesn't get the crazy seasonal signals. So you must be wondering what happened after 2010. Actually, you can go on Google Earth, and if you find this point, you can look it up, and you can see the tree. You can go backwards through time, and sometime in 2010 or 11 or so, the tree's suddenly gone. I'm told that GPS people who got angry about this came out in the dead of night and chopped down the tree, but these are just rumors. Anyway. Yes, so that's another thing. InSAR changes on the lower left, PHLB. InSAR seems to change the pattern, whereas GPS does not. GPS continues kind of in the same direction. The point of the tree story really is not that GPS is bad and InSAR is good. The point is really that GPS, sorry, there's a creature. Sorry?
Leaves of that tree is very heavy.
What is heavy?
Leaves.
Yes, yeah, that's true. Thank you. The point is that GPS measures local effects. And those local effects, GPS measures displacement at exactly one little point on the ground. And that point might be doing something, whereas InSAR resolution at its best is somewhere around tens of meters. So GPS might be doing something slightly different just because there's something local going on in that particular spot, and the overall deformation over tens of meters might be different from that. So the signal is not that different. There is a change. As you can see in the plot with PHLB, for the InSAR, both corrected and uncorrected have that change in trend. So what it is, I'm not really sure, but it must be something. There must be a difference between. You have to check on Google Earth, yeah. There might be a forest there, I don't know. However, this is not the case for CCCC and RAMT. So, and those are not that far away that you can blame bad orbits. So don't undermine my lovely GPS tests. again, if it were satellite orbits, that would be, you would see that in all of the time series.
No, because sometimes these orbits are like non-linear, so you know. If you look at
That's another research project that you guys can explore.
Does the
Yes.
GPS track the ionosphere direction?
Can.
I think so many people compared that to InSAR, correct InSAR with GPS ionosphere, right?
The question is, does the GPS track ionosphere delays? Because GPS is dual wavelength, so it can actually compute what the ionosphere looks like at each point. And can you use that to correct the InSAR data? Unfortunately, and this is the same for the troposphere actually, there is a calculation. Yeah, unfortunately there's a difference between the GPS measurement, which is basically a zenith measurement, and it's kind of an average over the sky, as opposed to the InSAR measurement, which is line of sight. And that's why it's been very difficult to correct, to use GPS atmospheric measurements to correct InSAR data. Okay. All right, so if you run SBAS on your, I kind of already went over this. If you run SBAS on your, from your GMTSAR installation, this is what you'll get. This is kind of these are the inputs you might use. But from before, I told you about the required inputs, the number of interferograms, the kinds of interferograms, or the list of interferograms you're using, list of scenes. In addition to that, you can use, you can input a smoothing parameter, as we discussed, the lambda. You can, and there are a few parameters related to the atmospheric correction. It's actually an iterative correction, so you can enter a number of iterations. I would say 3 is a good number. You can enter the wavelength of the radar wave, and I think this is if you want to convert stuff to meters from radians. Is that correct? If you want a scaling factor, you have to specify that. Okay, so that one is not an optional parameter, even though it kind of looks like it. So you have to specify the wavelength, otherwise it will assume ALOS, which is maybe not true for you. You need the incidence angle and the range distance from the radar to the center of interferogram. I think these are parameters you can find in your what are they? Okay, right, so these are, right. Okay. So these are, right, these are for the DEM correction. I told you that these have to do with baselines, satellite baselines. And for that same reason, you enter your location of your DEM, the name of your DEM. Yeah, so these are all things that you may want to play around with and you may want to try.
One thing about this program is that it can use a lot of computer memory, because it has to store the dimension of each unwrapped phase times the number of interferograms. It's the most. So I can like have, I don't know how much typical number of interferograms, 500, 1,000 times 3,000 times 3,000. The numbers get big.
So the summary of that comment for online folks is that be careful, this program may use a lot of memory.
Get a bigger computer.
Get a bigger computer is the advice, the expert advice. If you, yeah, yes. So in the end, you end up with these displacement GRD files and a velocity file.
Also, if you are specifying the minus ATM, it's also going to be your atmospheric phase.
All right, if you're specifying the minus ATM, you will also get atmospheric phase screens or phase maps, whatever you want to call them. Yeah. So I'll show you a couple of examples. So this is from this is from Sentinel. This is from Eric's and others' paper about the Serra-Pareto geothermal field. This is going to be a movie, and on top you see what's happening from SBAS as you look at cumulative displacement with the atmospheric correction, and at the bottom is without. So you can see there's a lot of drama going on there in the bottom. There's all these weather patterns moving in and out, and on the top, mostly you just see the deformation from the geothermal field deepening. There's substance going on there. So this isn't bad. These are examples, kind of zooming into that geothermal field, of what the uncorrected time series look like on the left. Then the estimated error, atmospheric error. Notice that the actual deformation from the geothermal field is not in there. That's good. It's just atmosphere. And then on the right, you see the corrected SBAS time series. Snapshot. This is a snapshot. Yes. After a certain amount of time. This is another example I wanted to show you. I wanted to prove to you that you can also recover nonlinear signals. So this is an example from the San Andreas fault. There's this event that happened on September 7, 2017. And these are time series, differential time series from different sides of the fault. So if you look at one side of the fault and then the other, there's motion relative to each other. So the example we saw with the Serra-Pareto field is good, but the signal there is quite large. It's a couple centimeters per year. These signals are only a few millimeters total. So we can still recover them. So this is a map. This is the San Andreas fault. San Diego is somewhere over there. This is if you take this area and you turn it on its side, these are the displacements. The blue is on the top, moving in one direction. The red is on the bottom, moving in the other direction. Fault parallel. And the time series are calculated, these T1 through T5 points. So the cool thing about this event is that it was actually triggered by an earthquake in Mexico about 3,000 kilometers away. So, and we can observe that now with InSAR. So I would like to finish with that and take questions. And this is ice cream for dinner. Ice cream. Yes. Okay. Got it.
The middle line is sort of amplified a little bit to the back.
Yeah, I can see it.
Yeah. Yes.
Your method of atmospheric correction, you said you have to do it at the correct time, same time. So if you don't have that, choose sort of like interferogram or.
So you choose. So there's the code. The code that's built into GMTSAR, in the SBAS code, assumes that you want to choose a time period of 90 days, 70 days, 70 days before and after. Yes. So within that time period, you want to take interferograms within that time period, and you want to subtract them from each other. The code also, I don't know.
No, I was actually talking about.
Yes, so I have it is incorporated in GMTSAR. So that's what we were talking about. There is a standalone, I have a standalone code. And what mine actually does is it will optimize the time scans to make sure that they're equal. So it will kick out interferograms that don't fit in. Yeah.
Have
We
you
can.
done your atmospheric analysis using X1 data?
Which one? Oh,
So
for
you
the
did
same
it-
area?
Well, not the same area, but I mean the same kind of analysis that you did for your thesis. Have you tried that with Sentinel?
Well, we
I mean, I know we do it all the time. Have you analyzed?
we did that for this.
Yeah,
Yeah.
not the same way.
It
have
isn't
you
the same
compared
way.
Weather model.
Oh, have I compared it to weather? Have we compared it to weather models and GPS? Yeah, we did that for the SCEC work. If you remember, there's a SCEC community geodetic model where we did comparisons with GPS and with for velocities and for time series. Compared with weather models, yeah, we're kind of looking at that now. Any other questions?
Ice. Ice.
Ice cream. Thank you.
So I think it's tea time now. Large cookie time. I can't remember what's on the agenda. I think we just keep working. Is that it? Keep working. Remember, tomorrow we're going to be entertained with a lot of interesting presentations, results.
So how we're supposed to hand those over
Sometime in the morning, like you could put them in this Google Doc. I'll send an email later on with a link to the Google Doc. You can just put them in the Google Doc.
You have to send to our Gmail.
Oh, Gmail. Okay. And if it doesn't get there, I'll just get a memory stick and get it. You can work until the very end. An earthquake. I saw that.
Same earthquake, but with different local angles. We did descending and I did ascending. Oh wow! And they look different.
Yeah, sure look different. Yeah. Okay. You should ask yours. Here is the expert on these kinds of things in this cat. Because, of course, they're the same earthquakes, so the ground is the same.
I think you have to be
Yeah.
well founded.
All over looking. So you need a model. So there's a modeling program. You run that now?
I don't know. Yeah. I used to. I moved to the city.
Do a very crude model. Is this a strike shift fault?
It was a very high angle.
Even if it's strike speed,
Did you unwrap the phase?
I did it for this one.
Yeah, I think that was pretty accurate. I didn't see anything in there. I didn't say. So this will be very different. And those two will give you the.
Rob did it with halos, and he got a clear uplifting.
Maybe the halo was it a descending halo? No, but what did Rob do? So, yeah, so the ascending and the descending will look. So maybe they're both. Yeah.
This is from the Japanese group, so I think it's Alo. Yeah, Alo's group, and it's the same event.
That looks just like here.
Yeah, mine looks like his, like theirs, but Chanda's look like letters.
Because those are different look at. That's neat. So you can unwrap the phase and take them off.
If I told Rob that it's almost unfair that he has become this easy next to all the
Oh yeah, anybody can make an interferogram. And now you have to do the interpretation. It's the hardest thing.
The problem with all it was,
Was that radar sat data? ERS. we started WinSAR, our whole goal was to buy data for this group and then share it. They spent $500,000. Yeah. Oh yeah. Yeah. And the computers are so much faster. So this used to be a mainframe. I just want to check to see what we're supposed to be doing. Okay. Oh, no, I didn't finish that. Okay, I gotta do that. Oh, that's nice. Is that one?
It's just on the second.
Yeah, that's great.
That's what's the one. Yeah, I tried to do that used to because it's so cheap.
As you can also see,
so actually just three. I was thinking of process. So it's on that. Yeah, I won't. Again, I'm actually unwrapping, which will take a long time.
And then you get this difference.
Maybe if you can try. Yeah.
Yeah, I think we could have one of those.
So that works. It's a double difference.
Yeah, that's what. I think that's it.
So it's a double number.
Okay.
So it's, I'll try to remove the ice flush. Well, we're here's the case. Difference in the model. But you could, I was saying, you could.
I just have one question about the yeah.
So you run that if your computer can handle it.
Yeah.
Parallel.
Okay.
And then you could even unwrap in parallel.
Yeah. I didn't try. I was still I was thinking so
Yeah.
you're all that.
Well, he wants to know whether to run in parallel.
Before.
Sentinel. Well, whether his machine can handle numbers.
How much? Well, the recognition is no, but not from because it's not sitting on the memory right now. Yeah.
It's also running time. I've even running on I've even running on probably so
Okay. I don't have enough as well.
Yeah, you don't have it. You only know the track number and base, but you don't know where it is. It's possible that the images are off, but it's not exactly.
It's the same frame with some direction. Along the okay. Because I think they have to be called, I try to deal with these. But the same frame, the way I'm using. Well, it's only. Yeah.
I like very much. The longest legs. But otherwise, it's still pretty cool. January.
Okay, you can have two.
No. So this is just a copy that
Yeah.
This is hard program design. Yeah.
If your computer can handle it, yeah. As long as they're all in different directions. Yeah.
So
You run this thing.
I tried.
Down and back.
I'm running them so it's.
So I mean, just run top minus OCP and tell you how many CPUs you're using and what percentage.
I mean, I could show you what so
Max
I
out
do
and do more.
get my stack.
Because the Mac has, like yours probably has,
I always check it out.
they're probably around 7 jobs. So
So like if it's all the same. It's a thoughts.
So I think it's
4 by 2 size.
right at it.
Yeah.
Oh.
No, I need to on.
Well, because the one that works is someone else. I gotta go to my office. Her name is Cassia. The last name is yeah, it'll be on the UNAVCO site. Oh, you're getting grab it. Yeah, there's a whole new one you can get. Almost new. Oh, sorry. Yeah. I know you guys also work on nuclear gas, trying to figure out where that's like.
It's never had a problem like this. It's that line I want to do a batch process. So it's I mean, I don't mind. But just to follow the yeah, but I mean, I know. So what I do is separate. So they all have like
Yeah, because we didn't have that.
no, but you have out. Yeah. So
Yeah, and one of the problems is it's not putting the data. They can only do that in SLC. And Anders was trying to figure out how to use it. Did we ever? I think it was more
no, but I'm saying like, I don't see. I don't know. So
one of the problems is like
Also,
Like ALS too. ALS too, they can split. Oh yeah, just the dropper. Yeah. We don't have any. What's good? But I think this one.
So that will track you. Yeah.
Okay.
Okay, so I don't know.
Did you find a DEM?
Yeah, to download maybe yours. I thought China was reaching slightly different results, so when I showed
Yeah.
there are like two patterns, and I don't see that.
We could probably discuss it.
Oh, yeah.
Yeah, this one is this was a Windows PC. This was years ago. Through Windows. They put CentOS 7. And CentOS 7, you get GMT5. But you have CentOS 6, it's GMT4. Because the read of GMT7, I mean, Yom install. But you see that they were slightly interesting.
they are interesting. I can tell by the looking by the shape of
China, this will be a third frame. This will be a third frame. What is the that low? So you have 30.
Okay. I mean, I'm running after that, I'll take our
34.6. Some of these ones not going to have. There we go. So,
and now you also have
that's the one that I did. The one that I did. Frame 74, 72.
Also remember when you go sending in assembly, the different shadow is different.
Oh, wait. That's the one you did, right? Oh, this one is hours before the earthquake.
Twittering?
No, not yet. Oh, 400
What?
400 people died from this.
Oh, no, we're in C#. That's
Yeah, exactly.
So the first one is sound, and the next one is distraction.
I think it's already been on. Which one is this? Oh, this is green. This is like
Yeah. Oh, yeah, yeah. That's right.
Have you got any to work? You don't get anything. Yeah, that's a good one. No, that's right. What exactly you were? It varies from, I did this example. It's not.
So I just created
Like range. This one has. And then the And then you go. Now that you've got one, I would just get rid of the green. Is there an area?
All right.
Can we go there? Maybe there's a pipe. So the only way to use water things. Is there a paper?
Oh, I see.
This is goes before.
Oh, I tried that also.
Has anybody had?
No, I remember it was.
And where's the response?
So essentially all of the
You've already done that. Oh, okay. So, but let's make sure we get it big enough.
Yeah.
Because it's going to be a side area. Or we could just do it.
All right.
I don't know. So when you,
Okay, so,
yes, after you download it.
you know,
Yeah, but there it has, the machine there.
oh,
Just that. You don't want to have to use
yeah. The thing is now, I mean, like this is normal. But the thing is working.
Make it directly.
Oh, actually, that's why.
How do we go there and delete all? Let's drag these.
Yeah, so once this is.
It's just going to the bottom.
Yeah, that's what. Actually, it only uses one before. So this is something that shows up. Exactly.
So after we have to extract it.
Whatever it is.
It's gonna be a lot.
For your SBAS.
They're all pretty small things.
I don't know, I haven't really done much. It's also.
So, I mean, you can run it on.
Oh, no. I see.
When it first came out, This is the way. Right now, it's running on 3 GMTs. In other words, they're still running the so if they don't want to run that, okay. So there's 2 ways you can do this. In another parallel window, you can start doing this. That's what.
So you get a bunch of
But what I need to do and then I would just and then we go back down. So here's type RV. That's those jobs. I don't think I'll do this.
Yeah, especially the sequence. That's what I read is that. So light is like, so it's it doesn't matter if
You say that.
yeah.
So that's the higher. Oh. Yeah. Yeah.
No, I wasn't.
But it's not it's not like walls are. Yeah.
Yeah, I always.
I hope so.
Scratch.
Oh, yeah. So, that's also probably
So, yeah, so it probably has in here, you couldn't find it. But this is just like,
We're gonna look at the line when you go into Topography, they want to say won't say so I mean, this is
So yeah, so yeah, so I don't know. I don't know.
Hey, Rob, I just calculated so it's still good. We're gonna get. Yeah. Hey, oh my God, he's close.
Oh, it's over.
Yeah, but I wouldn't say it's in the low 60s. It's about 70. Yeah, it's doable. You won't die of hyperthermia.
Well,
It's not Massachusetts.
You're thinking hours.
Yeah.
Yeah, never doing it warm here. Maybe it's September.
So what's Massachusetts? Way worse. Even in
Yeah.
it was probably I think
try to get it in one spot. So in a few minutes we'll be able to get it. No, yeah, this is a lot. It's one of the big problems. The way you stick the libraries. I think it's a sort of order. I forget which one. I don't know. I don't need this one. Everything else.
Yeah.
Yeah.
I don't know what happened. It was probably some stupid need copy stuff. These were SNAPHU. Yeah, sure. And the things are crashing.
Turn on the transparency so we can see.
They were sending me text, a copy of it's going. Well, they use the tablets.
Oh, no, I'm sorry. Just click on it.
They always indicate whatever. My wife always has to.
So really, you're
Yes, I'm done. I'm done.
The small shop to the side, maybe the second you go outside.
I'm done voting. When I go here in the back, it's 12 minutes. Yeah, but the Wi-Fi was competing here. When I go here, I was downloading the frame.
So for now, that's the final form. So let's use that later on. So the next thing is
Oh, I had some.
Yeah. Right. Yeah, these are fine. I got it. I didn't understand that part. It's obvious. That's a way of not having to do a lot. So let's go back to your unpack.
Yes, yeah.
Okay. You don't need it. So let's throw away this. Right. Now you have that. Now let's get the radius from the line.
And then do I need to replace this text down here as well?
No.
If you're running
Just run. Okay, so what's going to happen is, this is right, we'll put a 1, even though we don't really have, that's going to be parallel. So what he said, start this going, and then what's going to happen is we're going to have to pull it up. L is going to be up to
learning a few times.
It's not really living on this record. Oh, no.
Oh, really? Okay.
Into that state direction. So rather than a copy then you go into that space and run a very similar. But they are.
Actually, InSAR, you can have
Oh, yeah. You can oh, okay. So next time we go,
People like to go.
But they still doing it for free. also really color with. So you can replace them. And the radar one is kind of working as so the radar is on horizontal and then it's running out. So if it's actually, I was just trying to bring this line so it's when you're looking for ready for it's very easy to find, but it's also you're gonna see rain going down, but also you can see so this kind of feature.
So we ran the one right? But it doesn't, it made 3 files. It didn't make sense. They're still running. In the raw drive, they want.
Yeah.
So now,
But it's like sort of water something at each cell. It's a weird machine.
So,
yeah, you ran this. You don't want to kill 100 meters. I don't know.
no, we didn't kill it yet. No, we didn't do anything.
Yeah.
We're waiting for this generator. We think that we need. We're waiting for generator.
There's no vertical
We didn't want to kill it.
There are few, there are many.
Oh, maybe.
So that's why I gave you if you check the command that you need.
It was in going back to the
Yeah. So clouds, because the rain provider, they will
We all like soft chargers.
I don't know how high they're shooting. But they should be shooting. You're gonna lose color. So we are shooting at an angle to the sky. Oh, there is no. We don't have. Basically, I don't know what exactly the range, how long the range is. I can find it all. One microsecond. That's in that same mile. You might just get it. Yeah, every time I shoot, that's the one.
Oh, okay.
It's all, and because you're PRA, so you're doing a lot of shot. Yeah. But the PRA might be. But like I said, they have to call it maybe.
Yeah, I was wondering that line.
Everybody's trying to from here. Here's what they call. I'm not gonna go. I'm gonna go. Then you can confirm. Then you can see. You might need to. I have to go home, so I will.
Yeah, it's a,
if you need something like you know, they're meant to go back. It's like they're this is very old technology. I can just listen. What these guys they have is like my power. I don't know what. For radiometer, there's a program for ETL and for they have a so for radiometry, they do expand 30 gigahertz, 20 gigahertz, something like that. Some are water, some are water. Once every month, But then you remember that we always have some rating problems.
Yeah. Am I looking for the actual file?
That's coherence.
You want to know coherence, yes, it's very bad.
That's why. Vegetation, UNAVCO is a I guess
Yeah, that's
it's
what
just
we're really using these
different,
steps.
just different. Okay, mass of the green, right? Unwrapping.
So,
Oh, so. There's some things that will demarcate us.
He might help somebody who also platforms. The idea of drawing people that what you know that we will go.
Oh, no, yeah, probably not some kind of. So this is my
It's funny that you can unzip it. The unzipping doesn't.
No.
oh, I think I got it wrong.
well, I mean,
Yeah.
Yeah, that's awesome. Region is good though. Coherence. Region is good.
Then you have to run it and then kill it. Then you run another one.
It'd be good if you could do this one. So what you'll do is after you run this, you're showing frame, and then you go into the F1, F3 direction. Run. It'll be good.
Yeah, it is. It's going to take a little while.
Okay. I'm sure this pair will be not. So, like this is begins. Okay, so I guess you could all take a sabbatical.